Okay. Um, Pretty much, I am promising to myself I will do computer networking at university next year. There's not really any requirements left for me. Um, I do want to be very proficient already while I'm there, and I want to be able to make money via crypto before that, like as in have a lot of knowledge. Um, Mainly about trading new launches on Ethereum. That's my kind of specialty. That's what I like to learn. What's what I've been looking into, and utility plays. So the logic would be I my skill set would be in new launches in Ethereum using query trading and filters and I guess personal filters and just getting really good at spotting new good launches. And I do think it's a skill that you can get good at because there's patterns because people are creatures of habits. And essentially what you're saying, if you don't think there's patterns in the market, you're essentially coping and saying people are random. No, of course people follow patterns, developers follow patterns, and you can spot those. It just takes, I think, a lot of time to get good at. So, and the money I make from that, I would siphon into utility plays when the market is like when they're at a premium, right? If I think, nah, the market is kind of just like the absurd highs right now, I wouldn't, and I would just probably just send this to stables or to the bank, my profits. And I want to just do computer networking and probably kickstart a career in that. Why did I say probably? Here's the thing: don't I like learning, but I know the reality of jobs and stuff, even entry level. Um, and in Optimal, you always work for yourself, so you can start some type of business that leverages your skills, or you do something, some work for people, but you work on your own time. You don't accept any disrespect, etc. That would be the optimal world, but I need to be very skilled to do anything like that, you know. Um, so yeah, when do I expect? I expect in Q4 that there will be a rebound and the market gets quite a bit better, and new launches get quite a bit better, hopefully for Ethereum as well. Because again, people have these crazy predictions right now. I'm not sure how true they are. Obviously, like 10k Ethereum, 6k, 7k, by Q4. If that happens, if that plays out, like if that, because right now we're already kind of rebouncing quite heavily, actually. Even BTC still very much below what it was at. If we make a parabolic move towards those levels again, shit will be pumping like crazy. But again, it is just speculation here. ETH has kind of recovered, kind of, because again, we're still down quite heavily from the almost 5k all-time high. But people think we're breaking this easily, and they're shooting for targets in the 6k plus ranges. And eventually, people expect a, well, not in December, but in January, Q1, I guess 2026, the bear market to begin. Most people. When I say most people, I mean, like I said, I always consider the average opinion of the smartest in the space, or who I consider, and I just think that's decent probability. And I also look at their arguments and stuff. Benjamin Cowan is a good one. So yeah. My goal is to make enough money in Q4 to sustain me. Again, sustain me. I don't really have much to pay for at all at the moment, which is good. And then, I don't know when the bear market starts. No one knows. Maybe we get an extended bull run. The skill of trading Ethereum new launches is my final dance. Obviously, is where I make most of my money from, I hope. And beyond that, just get really good at computer networking. And I apply for jobs in computer networking. I need a couple more certifications. I'll do uni next year. And that's all sound. Because here's the thing. I would not mind working in this field at all. I really like it. But I don't lie to myself. I know people value freedom the most and aspirations to do great things. But most of the time, that doesn't mean a job, right? That just means researching on your own time, getting good at something. Depending on the subject, obviously. But yeah. I'm a studious person. I enjoy learning, so I thought, why not? So, we are actually going to go back from the very basics because it's been 8 months. Now, of course, I already know the basics. I think I should still. I definitely do. And the CCNA is not like the basics, I would say. It's like pretty fucking, I mean, it's pretty difficult. Most people study at least a couple months for it. So most people, when they think of basics, think, oh yeah, I can watch a couple videos and I know the basics. CCNA is not like that. Now, obviously, I'm not going to retake the CCNA, but the info in this playlist is good. Just a recap. I do want to kind of go through it quickly. We'll do a 15-10 strategy, starting with 10, and then we'll start. What is a network? Okay. I want to try to explain this in a way that people understand, okay, and why it's important. The world is more connected than it ever was, okay? Now, the implications from that are massive. They are a complete economic shift. People no longer, and societal shift, like cultural shift. Everything is connected. Maybe directly, indirectly. Usually through something we call ISPs. Those are those little green dots. Now, internet service providers operate at three levels. There is the ones that connect directly across borders, like across the major players, essentially, right? Now the way they connect is the connection you see here. It's always high speed fiber. What is fiber again? Fiber is the fastest type of internet. It's essentially light. Why is light so fast? You can think of it like, the best analogy maybe is it's weightless, it's smooth, it goes through space and time instantly. There's no friction. Whereas electricity and all that shit has to like almost bounce. I don't know. Think of light as just a continuous beam that can run in a straight line. I don't know, it's a decent analogy, I think. Now when you say cultural shift, more people are using Discord to make friends instead of real life. More people are on IG, stalking pages instead of talking to them in real life. More people are gaming instead of going outside. Yeah, well that's gaming and Discord technology. That's different from a network though, right? No, because all of these, the core function of all, the core capability of all of these is almost instant feedback. Especially for FPS games where it matters the most. So you'll again, when we talk about instant, the most instant type of feedback is something like UDP, which stands for Universal Datagram Protocol. It is essentially the high-speed way to, or the instant way without some type of, without some type of handshake, which is a core characteristic of TCP. But UDP doesn't have security then? Like a handshake is used for security. UDP does have security, but it's largely just... It depends actually, sometimes it doesn't. Because there's so many packets that contain such little valuable information. The altering of one is like kind of weird. Like, and I imagine this is also why you hear like microphones, phone audio is often poor. But the website web page you visit is 101 how it's supposed to be. Okay. Why? Because there's a verification element, handshake. Handshake is proving who you are, yes. But every packet is checked for alteration. Now that's not a core element of Now we're just getting started with this, by the way, because I truly believe that with time, no matter what you want to happen, people will move towards a more virtual reality. And I think the end game of that is some type of metaverse. Not what Mark Zuckerberg imagined, maybe, but what, like, every indicator to me just points to that direction. Roblox spiraling into fucking popularity with newer kids, and it's a virtual world. It's literally a metaverse, but like without the in-depth and, you know, good graphics and certain real-world characteristics. But it provides experiences, and that's the main thing that determines how well this thing will do, or anyone who presents an idea of the metaverse. And of course, who presents this, like your ethos and stuff, and your pathos and logos. Okay, so whenever you open a web page, a couple things are happening. You're using a bunch of protocols. We'll give an example now of TCP, right? If you, Bobby, sit behind your computer, and I want to provide some kind of cool things you can maybe alter? Yeah, let's do that. So you open maybe google.com. So to list all the protocols involved, there's DNS, there's World Wide Web, which is kind of a protocol. Is it? Yeah, it's a protocol for sure. There is I think this is where post, that defines things like post and pull and like shit like that. There's TCP, there's SSL or TSL, probably TSL because it's not deprecated. Now what order? Well, we'll get into that in a sec, but there's IP, obviously. There's MAC. Yeah. Is that called MAC address? Wait, layer 2. I mean, I think those are better summarized as layer 2 protocols. There is HTTP are usually the secure version, which uses, again, TCP is like the bare minimum. On top of that, the security layer is okay. Now, what do you mean they're protocols? Well, what is a protocol? A set of rules that a computer follows. So it's built in? Yeah, it's built into the programming. It's actually built into the firmware. The layer 3 stack IP is built into it. Layer 2 as well. Now, a lot of things are fully software based, like well, layer 4 transmission control protocol also is actually firmware based in the network stack, I think. It depends though. I don't know how to describe this properly.
I'm playing online, and the guy I shot isn't just in the game, he's actually playing a game somewhere far away from me. How did my bullet get all the way to him? Actually, come here with me real quick. Come here. So, that bullet has to fly over this Ethernet cable all the way down here. Come on, let's go down here. It goes into my wall jack here. Come on, let's go. It goes into my IDF, to my network stuff here in my rack. Comes through my walls, to my switch, to my router and firewall, then to my modem. And where does that go? Come on, my stuff. Come on, let's go. It goes into my IDF, to my network stuff here in my rack. Comes through my walls, to my switch, to my router and firewall, then to my modem. And where does that go? Come on, come on. Goes to my AT&T fiber box, and then to the internet. Okay, the internet. You probably saw that coming, right? Like, duh, Chuck, we play online on the internet when we play Call of Duty with other people. But what happens after that? When I fire that bullet, where else does it go? I've already shown you how it goes through your entire network. This is what you have right now. If you're playing Call of Duty online, this is your local area network. But what happens when we go outside your home to the WAN, or the wide area network? Let's see. And the internet will just be more routers, just someone else's routers, hip hopping across great distances. And that's all the internet really is, just a bunch of routers connected. But of course, it's not just routers. You'll have switches here, firewalls, just all kinds of stuff in all these different networks. But the cool thing is that in the blink of an eye, as fast as you can fire a bullet in Call of Duty, that's how fast things are going across all these routers. Until finally your bullet flies all the way to the Call of Duty servers. But hold on, not finally, not yet.
The blink of an eye, what does he mean by that? Well, I'll say that's fast, but how fast is it actually? Like what? Well, they have to go through the OSI stack, process it. Now, your processing speed largely also depends on your device. Like, certain devices have a lower. People don't notice. Like, your internet potential also depends on the hardware of your device, your network interface card, etc.
Because your bullet has made it to Call of Duty, but now Call of Duty has to send your bullet to the guy who's about to get shot. So, again, we go back up to the internet. Bam, back to the router. And this could be another path, hopping from router to router to router until it finally arrives at my brother's house. Because he is the one I shot, and it will hit his modem, his router, his switch, travel through his Ethernet cable to his PS4, and he gets shot. Crap! Now, why did I show you this? Why would I show you how a bullet can travel across the internet? Well, I did it as a test. What I'm hoping is that if you saw this, you would go, wow, I want to know more about how that works. I want to do something like that. If that was you, this course is for you. The CCNA is for you. Because what I just showed you is what you'll be learning in the CCNA. Networking, how networks work. Now, if you look at this, the networking we have now is pretty complex. But the goal is the same as it was 20, 30, 40 years ago. I want my computer to talk to another computer. I want to share data with that computer. I want to hang out. That's all we want to do. And that's how networks came about. It was one computer saying, hey, I have all this data I want to share with another computer, and I can't do that right now without a lot of effort. So you know what? Let's figure out a way to connect ourselves. And that's where networking was born. We can still do this, by the way. You can use an Ethernet crossover cable just to connect two computers together. But Mark, he wanted to talk too. Mark over here was left out in the cold. Oh, hi, Mark. So in comes switches. And a switch will allow us to connect more than one computer together. Doesn't have to be a computer, it can be a printer. Oh, by the way, just so you know, I'm glossing over this. There's a lot more involved. Broadcast domains, MAC addresses, VLANs, all kinds of stuff with switching. So just know this is just the tip of the iceberg. But if you like this, you'll like the other stuff too. Now, this is a network, and a switch facilitates that. All these computers are connected together, they're inter-networked together, and they are having blasts, talking to each other, playing games, whatever. Now, a switch can only handle so much before there are too many computers talking, too many things talking all at once, and he's like, I can't do this.
How much is that? Like, depends. 24.
So what do? Well, we get another switch.
But I don't think you should maximize. I mean, you can maybe. Sure, why not? I mean, there's that many ports, it will work. But so do you connect the switches then? But what do you want? What do you want to happen? It's like, yeah. You can connect these switches, or at layer 2. Is it better? Yeah. I mean, this is what I was taught, right? If I remember correctly, if you have switches, you should connect them. Not really. Actually, that's not true. That's wrong. It depends. If they're on separate VLANs, which they probably are, then you need a router anyway to so this is all one network, and this is one network, and the router needs to route between the networks, obviously, because each VLAN. But if they're in the same VLAN, then sure, you can connect them at layer 2, and it's fine. And if they're layer 3 switches, you can also connect them at layer 3 because they can communicate. That's the way I understand it.
Easy enough, right? So easy. And we connect more computers, and they have a blast. They're having a good time. Yes. And yes, the more computers I draw, the worse they get. You probably can't even tell they're computers anymore. I should probably label my switches, right? Let's just call them switches, so you know what's going on. Now, what we have here is essentially two networks. Let's call this network 1 and network 2. We got a problem, though. What if Bob over here wants to play a game with Mark, but they're not connected together? How do we solve that problem? Well, that's where routers come in. Routers. I'm not going to draw one. I'm just going to bring one in. A router will help these two networks talk. That's what routers do. They help networks talk to each other. So we connect our switch up to our router. Bam, bam. And a high-level view, extremely high-level view of how this might work is Bob's like, hey, I want to talk to Mark. So he says, Mark, are you here? And everyone's like, no, Mark's not here. So Bob's like, huh. Well, maybe he's over here. So he goes to the router and says, hey, router.
Yeah, I do remember. I visually remember all of that.
Is Mark anywhere? Do you know about Mark? And the router's like, yeah, I think I might know where he is. Bam. Hey, Mark is over here. And now Mark and Bob can talk to each other. So where does the internet come in? Well, this might be just one section of the internet. So we'll put them down here. And we might have another router with another situation. And by situation, I mean another switch with a bunch of computers who just want to hang out with people and talk and play games. And we connect these two routers together. And the internet is just this times 1,000. Now, again, I've got to say this. If you were to pop the hood on the internet and look inside, it's pretty complex. Like, there's a lot of stuff going on. So keep in mind what I'm saying here is very high level, but that should be exciting to you. Like, wow, I can't wait to learn.
What is an example of something complex that he's talking about? Well, the more basic thing would be inter-VLAN routing, which is just where you have multiple VLANs because each is a different network. They have to connect. It's called inter-VLAN routing because they talk between VLANs, and each VLAN has to be a different network. It has to, yeah. Because otherwise you don't know what VLAN to send to. And I think it just sends to all. Problems will arise.
More about how all this works, and we'll definitely cover that. Okay, so we looked at our switch and we looked at our router. What about this guy? What's a firewall doing? Well, simply...
What's the firewall doing? Well, the firewall is just there to provide some protection. Usually, again, this is theoretical obligations. So these are functions, right? There's always a firewall. Often it's software inside the router. And it filters and has certain rules of what to allow and what not to allow.
He's protecting you. He's protecting your network. Now, as you may know, there are some bad people out there, some bad dudes that want to attack your network, that want to steal your information. These hackers are constantly trying to find ways to steal your stuff. And while they'll try to get into your network, a good firewall will keep them out. Now, again, with networking, routers and switches, we want to connect people, connect computers, connect devices, smartphones and smart lights and all kinds of stuff. And that's normally good. But then there's bad things, and that's where a firewall comes in. A firewall's job is to block anything that shouldn't come through or go out and only allow the good stuff. Now, I'm hoping at this point, some of you are probably going, well, Chuck, I don't connect anything to a switch in my house. There's no cables anywhere. What are you talking about? Well, you're right. For the most part, most of the things we use in our networks have no cables. And that's why part of the CCNA, you'll learn about wireless. But where does it come in? Well, here's how you would do it. Let's take Cameron's network, for example. I know that he has what's called a wireless access point, often referred to as a WAP. And this device is designed to broadcast the network over airwaves. Airwaves that your phone can connect to. Now again, many of you in your home networks probably have one device that has a access point, modem, firewall, router, and switch in one device, which is pretty amazing, which might cause you to wonder, well, why does Chuck and his brother have separate devices for all these functions? Well, first of all, we're geeks. Second, we do that because we are network engineers. And this is what you'll see when you walk into a company, because a company, they won't have one device that does all this. Companies will typically have a lot more people, a lot more things on their networks. So they'll need bigger switches, bigger firewalls, bigger routers, more access points. So they just need more, and they need more features. If you're curious about what I have in my home network and what my brother has, I've got links below. Now again, this will be a free CCNA course. CCNA being the Cisco Certified Network Associate. It is one of, and probably the main IT certification you'll want to get on your path to becoming a network engineer. What's a network engineer? Well, what I just showed you, the whole Call of Duty thing, the bullet blowing through space and getting to my brother across the internet. A network engineer makes all that stuff work. They design things like that. They make sure those things stay up. That's their job. And the CCNA will begin to teach you about those technologies, understand them, build them, how they work. And we looked at a few of those devices right now: switches, routers, firewalls, wireless access points. We'll later look at network controllers and where servers come into play. And we saw the Call of Duty server, right? But we'll look a bit deeper into, well, really, what is a server and how does that affect our networks? So free, what are you getting? I gotta make sure you get your money's worth. So I will be doing one video a week. And this will be a complete course covering every topic in the CCNA. Now, a large reason I can do this for free is because of my sponsor, Boson. Boson Software. If you've watched me before, you know I talk about them a lot. They are by far the best labbing and practice exam software out there for CCNA and CCNP. No joke. And they have other stuff too, but CCNA, CCNP is what I've used them for, and they're fantastic. That being said, I will be using them as my lab demonstration, and I will be throwing up practice exam questions throughout these videos. Now, real quick, Boson is having a sale right now, 25% off. It's their summer sale. So if you want to get Boson, now's the time. I've got links below. Now, if you have questions, hey, this is my first video. Just getting started, so I'll probably end up answering a lot of your questions. And, you know, I've been talking about the CCNA for a very long time on my YouTube channel, so I probably have answered your question already if you look back through my videos. Otherwise, I'm here to help. Leave a comment below if you have any questions about this. It can be about, hey, how long is it going to take to study for the CCNA? Will it help me get a job? Is this even worth it? I mean, I've explored that. I have the CCNA. I got it to become a network engineer. It served me pretty well. Well, guys, that's all I got. I am stoked, like legit excited to start this course. I can honestly say the CCNA changed my life. I know it's changed many people's lives I've talked to. It's one of those certifications that when I put on my resume, it did open doors for me to become a network engineer. So anyways, get your coffee ready. There'll be lots of coffee in this course. We're going to study, we're going to lab, we're going to practice, and we're going to get certified. I'll catch you guys later.
Okay. Anything that you missed that you didn't know before? Not really. I mean, look. I think. No, smart lights, smart shit. Again, everything that has an IP is part of a network. IPv6, IPv4. Beyond that, I don't really think I missed anything. The fact that conceptually it's just a bunch of routers connected. I mean, yeah, obviously. And yeah, like, so often I lack the ability to understand, like, why do, like, okay, we have these all-in-one devices that have all these functions, right? Each of these things is essentially a function that can be part of a device, because at the lowest level, it's just like firmware or software. But enterprises need separate devices, which is why you learn the details on how to set up these things.
This is day one of my free CCNA course. And a huge shout out to Boson Software, the official sponsor of this CCNA course. They are the reason this can be made available for free, so I highly encourage you to go check them out. They have the absolute best CCNA, CCNP, labs, and practice exams. Day one, we're not wasting any time. We're getting right into what is this? It's a switch. How does it work? Why is it amazing? Because it is amazing. And we'll even get a chance to lab. What does labbing mean? Well, you'll find out. We're going to use Cisco Packet Tracer to analyze frames and packets going across a network. And you're going to get a chance to enter your first Cisco CLI command. Let's get started. In my last video, we talked about what a network is, and we followed a Call of Duty bullet when I shot it from my computer, how it goes to my home network, to my brother's network, and shoots his character. And we went high level, like router, switch, firewall, access point, what are those things? But we didn't go too deep. But now, are you ready? We're gonna go just a little router, switch, Call of Duty bullet when I shot it from my computer, how it goes to my home network, to my brother's network, and shoots his character. And we went high level, like router, switch, firewall, access point, what are those things? But we didn't go too deep. But now, are you ready? We're gonna go just a little bit deeper. This is like one of those red pill, blue pill situations from the Matrix.
After this, there is no turning back. You take the red pill, you stay in Wonderland, and I show you how deep the rabbit hole goes.
You take this pill, there's no going back. We're going deep into the networking rabbit hole. You're gonna fall in love and never look back. Okay, I warned you. You're still watching this, that means you wanna keep going. Let's do this. Okay, let's talk about switches first. What are they and what are they doing? And here's one right now. This is a switch. It's beautiful, isn't it? Look at this.
Explain everything that you know, the details, the low-level stuff. Okay. We have here is a switch. In switch, it's a layer 2 device that are layer 3 sometimes. What does that mean? It means that it can route IP packets also, so it has that functionality at layer 3, which is IP addressing, essentially, summarized. So it can know when or where, or it can know that something is in, for example, subnet 1 versus subnet 2. This here are Ethernet ports. So this has seemingly 8 ports to be connected to. This is, I think, the connection of the actual configurer, maybe? Maybe not. This is, I don't know. Okay, explain everything. Okay, so we're going to talk about switches first. Where are switches? Okay, so switches are what you consider when, or what you think about when we talk about inside of a building as the furthest range it will go. That's not really true, but it's not. Well, no, not really. I mean, sometimes switches connect across a campus or something, which would be a campus area network. But the switches themselves, right? Again, this is not a switch, but this is a switch. Kind of looks like a building, but it has a bunch of ports. Why? Because it's what we will use to connect people at layer 2. That's not an answer. It's the device that will do most of the constant work and that needs to interconnect the people inside of a LAN or campus area network or whatever. Well, usually inside of a office space, or there usually is a bunch of cubicles, right? Or a bunch of people working, or right, most of it. There's a lot of things going on. So you can imagine that if a single retail device had to take care of all of that, and we're talking usually something like if it had to do wireless and then also provide some, this is not, the specialization always wins, I think, is the answer as well when it comes to large scale things. So in other words, the switch is the most effective way to do this, to get this shit done. Always has been. So oftentimes these are like yellow. Now there's the thing, there's more going on here. This can have security, port security. This has a port number, obviously. And usually there's somewhere around 24 on a like good switch. And again, this connection, they're now connected at layer 2. Unless it's a layer 3 switch, then well, they can be different VLANs. But what does that require again? Remind yourself, should become second nature. It requires then a highway towards a router. And again, so what does a switch do? It receives a packet. What happens? So let's say we're sending a packet. Let's say Bob sends a packet to Alex. So if these are in different VLANs, the packet travels over the line. Let's just over the line. Nope, sorry. What am I saying? First, it's like, where are you, Alex? And if they've never communicated before, Bob will want to know Alex's MAC address. So Bob broadcasts a packet. Broadcast packet. The switch, which also has a name, let's call it switch 1, broadcasts it to everywhere. Now, because this is in a different VLAN, actually, I think it will stop here because this port would be assigned a different VLAN, right? So this wouldn't even go over here. The router though would see, oh, okay, so this is trying to communicate with a different VLAN. Okay, let me send it to the right port, and boom, and then here, this is my MAC address, and then, well, I think the first packet would be together, right? So it ought get the message. Plus, it would give Bob the correct MAC address. What is a MAC address? MAC address stands for Media Access Controller or Control. It's essentially the physical identifier. Why not just use IP? I mean, everything has its responsibility, its function in the network. So why not just use IP? I mean, this is a silly question because at layer 2, which is, again, it literally identifies the hardware as well. You need it. But why not just use IP for that? Why not because it needs to be more unique. Or sorry, less unique, right? MAC address doesn't even need to be unique. IP does. Public IP does. Private IP doesn't. Private IP just has to be unique inside the actual network that the private IP lives in. Okay, so what else? Port security, port numbers, VLANs, inter-VLAN routing. And who has to know about inter-VLAN routing? Who has to know about that? Well, the device that does the inter-VLAN routing, which is the layer 3 device. In this case, the actual router, because it's not a layer 3 switch. So what are some common pitfalls of switches? Good question. Do layer 2 ports need to be enabled? They need to be assigned a VLAN. They need to. What else? They have the... the mesh network. Think about that. That's largely redundancy. Yeah. Well, when you need redundancy, it depends, right? Servers that are valuable, yes. Talk to me about servers again, by the way. Why not peer-to-peer? Why not peer-to-peer? Some things are done peer-to-peer, but processing of... Like, if everyone has to know that something happens, right? Like, no, there can be a host. Someone's given off the host, right? Like, I don't know. But...
Oh, love it. Now, if you watched our last video, you have a high-level view of what a switch is for. What's it doing? Well, it's helping our computers to connect to each other and talk and hang out and chat, send data. We connect using these Ethernet cables and we plug them into our ports. Oh, love that sound. Here, listen to this, up close. ASMR version. One of my favorite sounds. So we connect one computer, connect another computer, and assuming we have computers on the other ends of these, they're talking, they're having fun, they're playing games. But what's really going on inside of here? Let's pop the hood, let's take a look. Oh, and by the way, switches can come in many different sizes. Like this is an 8-port, and this big boy is a 48-port. He's beautiful. Why do you need 48 ports? Well, so you can connect 48 different devices to each other. That's why. Now let's first look at this guy, the Ethernet cable. All it is a bunch of metal wires. Like, check it out. Your computer communicates with the other computers via electrical signals, and these electrical signals go down these wires through the cable to the switch, and then it goes to the other computer. It's amazing. It's just electrical signals going in and out of these ports. Isn't that cool? Now, switches are amazing, but for you to really appreciate how amazing they are, you need to look at their predecessor, the one that came before them, the hub. He's disgusting. He's dumb. He doesn't have any smarts. The switch is smart. The hub is not. But before we had switches, hubs are all we had, and here's what they did and why they're dumb. Now, I want you to actually see how dumb this is and experience it for yourself. So right now, what I want you to do is go download Cisco Packet Tracer. I've got a link below. Sign up for a free account through Netcad, and you'll be able to download it. What is this? It's a tool that lets you build and play with networks, and so much more. It's amazing. So go download and install that. It's on Windows, Mac, Linux, and once you install Packet Tracer, I've got another link below for a Packet Tracer file, which is a lab I built that we can play with right now. So go ahead and download that and launch it. Do not get overwhelmed with all the buttons and options here. I'll walk you through every step right now. If you zoom in right here, I've got two networks. I got this one here, which is a switch, and my laptops. If I scroll over, I've got another network, and it's not nearly as smart because I'm rocking a hub. Now, a hub and a switch physically kind of look the same. They look like this. They have ports we can plug Ethernet cables into, but they're so different. Actually, we can look at a hub right now. Let me click on the physical button up here. I can click on my home city, my corporate office, and then jump to my wiring closet, and there it is. So you can see switch, it's got ports, hubs, got ports, okay? But why are they different? How would you like this? If when you sent a text to your friend, it didn't just go to your one friend. It went to all your friends. And then when your friend responded back to you, it not only went to you, but it went to all your friends as well. That's stupid, right? Like that, I would never use that texting platform. That's what a hub does. Check this out. And I want you to do this with me. So click on simulation down here at the bottom right. This is what makes Packet Tracer so cool. We can analyze the network traffic slowly as it goes through the electrical wires. It's powerful. Anyways, so don't touch that. Leave it there. I want you to click on Harry Potter up here. Laptop Harry. Then click on desktop, and then click on command prompt. This is very similar to a Windows command prompt. It kind of is a Windows command prompt. And what we're gonna do is we're gonna have Mr. Harry here talk to Ron over here through the hub. We're gonna send a message that we use in networking all the time called a ping message. What is that for? We use it to see if other computers or servers are up and can be reached. Kind of like this.
Ping!
Reply!
Ping!
Reply!
Ping!
Reply!
Now you may have noticed I've got a couple things right here. Layer 2 address and layer 3 address. Now what's an address? Well, if I wanted to send you a message, I might send it to your email address. If I wanted to send you a letter, I might send that to your mailing address. It's something unique to you that allows me to send something to you. Data, whatever. And in the networking world, it's the same thing. Now what does layer 2 and layer 3 mean? We'll cover that here in a bit.
I'm not going to waste my time right now and open Packet Tracer right now. Are you sure? Yeah. Isn't that a bad idea? No, because I want to get through this playlist, synthesize the information, and then do all the labs. Because again, I already know all this as a theoretical thing. I don't want to spend too long on this. I just want to spam labs essentially and understand them and play with them and tweak them and get really fucking good at that shit. Because again, what I want to do this year as a final project is create my own website. And to be honest, I think I've created one website like a year ago, and that was through like the help of a YouTube video. So, but I want to do it fully by myself, just as a way to fucking torture myself and show some initiative. Build the website from scratch. Now, obviously, well, you can't just build a website without knowing anything. But my point is, what I'm saying is, I'm going to watch a playlist, learn along first, like properly, and then fully delete everything and try it by myself and just trial and error at that point. That's how I think you learn best. So yeah, what's your opinion on hubs and switches and the relation there? Well, hubs are at layer 1. That's all you need to know. What does that mean? What does layer 1 mean? Layer 1 means that it can't even identify people. It has no idea. All it can do is send out information through all its ports. So a hub, Harry sends, hub receives it, and sends it out all ports except the one it came on. There was the input, and outputs it to all the ports, and everyone reads it. Now, if you're using something like HTTP unencrypted, where a single person, even everything would be shared, then no? Well, I suppose, yeah.
A bit. But just know that when I'm going to send a ping message to Ron, I'm going to be looking at his layer 3 address. That might look familiar to you. What is that? Well, that's an IP address. You're probably familiar with that, right? Harry knows that when he wants to talk to Ron, that's his address. That's his phone number. That's his mailing address. That's how he gets information to Ron, his IP address. So here we go. We're about to ping Ron. Now please make sure you have the simulation button checked. Not real time. You want simulation. There we go. Get your command prompt open. We're going to ping Ron. So I'll type in ping and then Ron's IP address, 10.1.2.3. Now watch what happens when I hit enter. Boom. A little envelope popped up. A little message we're going to send to Ron. And then notice over here we have a little event timeline where that message just popped up. We can see the play-by-play here. As we get more advanced and go deeper and deeper into what's happening, which will actually happen in the next video, we can click on these and look at some hairy details like, what's happening? Don't worry about that yet.
What's happening? Not really. Again, this thing can confuse you, but there's nothing really confusing. This is the layer, okay? So the IP is the outer packet, the outer layer. Why? Well, because we're not using HTTP. We're not using a layer 7 protocol. So the packet at best, again, the packet is encapsulated because it's built into the software, the firmware. Which one is it? You can't just say software, firmware, oftentimes, like I'm describing something like a packet is built into the software or firmware of your computer. Which one is it? Like when you say like, oh yeah, like computers know that's how an IP packet is structured. They know how the application layer has to be structured. Like when TCP, TSL, SSL, and all of that gets involved, it knows that intuitively. Part of its OSI stack. Which is the more accurate term? Would you say that the software of the device knows it or the firmware? Okay, so the software, the OS networking stack, and drivers knows how packet and protocol layers are structured. Right, that's more accurate. I need a ChatGPT. Networking ChatGPT that I still need to make. Let's close this.
Cool, we'll get into it. But it's amazing. So Harry wrote his letter. He's ready to send it. And if we click on this little advanced button right here, it'll take a step forward in time. Let's go ahead and do that. Click advanced. Boom. Let's do it one more time. Boom. There it goes. It's going across the network. Electrical signals firing. So now the hub has the message. In an ideal world, in a perfect world, the hub was like, oh, okay.
De-encapsulates, re-encapsulates.
Well, this message is for Ron. I'm going to send it to Ron. But
what do you mean de-encapsulate, re-encapsulates? Well, this is the information that was required to go from here to here, right? All of that was sent over, well, the Ethernet cable as electrical signals, as electrical pulses, which are really zeros and ones underneath, are interpreted at each end as zeros and ones as they're being sent. It's not digital, obviously, it's electrical pulses, but they're interpreted using some type of modulation technique. The hub reads it because it's a dumb device at layer 1, sends it out of all the ports. The
hub's an idiot. He's dumb. Watch what happens. Watch what happens. Click next, and why did you do that, Mr. Hub? You sent the message to everyone. Harry's just trying to talk to his buddy Ron, and now Hermione knows, and Malfoy knows. That's bad, right? Now watch what happens next. Remember, in a ping situation, Harry's going to send a ping. Hey, you there, Ron? And Ron's going to go, yes, I'm here. But watch this. Click next. Ron does reply, perfect. But then watch what the hub does, the dummy hub. He sends Ron's reply out to everyone. Why, hub? Why? Well, again, the hub has no smarts. He's got no brain. His job is just to repeat that electrical signal. Wherever your computer sends down this wire, the hub's going to go tss and send it out to everyone. This is how we did things for a long time. Now notice that over here, Harry Potter's got a green check mark going, yes, yes, yes. That message is for me, yes, yes, yes. But then down here, Malfoy and Hermione have this X, which means that most of the time, in a hub environment, if a computer got a message that wasn't meant for them, It would just ignore it. But, you know, that's if you're a good person. If you're a hacker, like I'm learning hacking right now, if you get a message like that, if you're able to see everyone's traffic, you're like, yes, give me more. I'm going to hack all you guys. Not a very safe and secure environment. You don't want to text your buddy something secret and all of a sudden all your friends know the secret. But now, let's look at the switch. He fixes everything. Go ahead and click on Reset Simulation. You can close out Harry Potter there. And let's scroll on over to the better environment, the switch environment. Now here, go ahead and click on Reset Simulation. You can close out Harry Potter there. And let's scroll on over.
So the events, can you explain them? They're literally events happening. That's kind of circular, my guy. Yeah. Like if someone does something, receives something, any kind of major action or thing that happens in the packet, in the tracer lab, I guess Harry sends, receives, these will all be events separately.
To the better environment, the switch environment. Now here, the switch has the same goal as the hub, just to connect these computers together so they can talk. So they're doing the same job, just one's really good at it. So over here, let's walk through the same situation. Johnny right here is going to ping Mark. Oh, hi, Mark. And we'll see what happens, and I'll explain how it happens here in a moment. So go ahead and click on Johnny, click on the desktop tab, and then jump into your command prompt. We're going to type in ping, and then Mark's IP address right here is 10.1.1.2. We're going to hit enter, and bam, Johnny's got a message ready for Mark. Let's click on next and see what happens. Next. Okay, there it goes. The switch has it. What's it going to do? Boom. So much better. Only Mark got it, and then when Mark responds, it only goes to Johnny.
Wait, the switch is doing layer 3 function? No, it's not. Wait, what do you mean? It's not. How? Johnny has Mark's MAC address. How do you know? Maybe it doesn't, but it would be able to ask that, and the switch would know what MAC address is associated with what port because it already learned that, right? Or well, maybe no, maybe it hadn't learned that, but it could learn it then by just broadcasting. It learns that. Okay, Johnny. It sends it back. Johnny knows, okay, it's cool. Okay, now I can send it. The switch knows where to send it out of, and boom. But it uses the IP address. No, Johnny and Mark use IP addresses. The switch just uses MAC address. Now, it kind of defaults to syncing if it's a layer 2 switch. These are all the same network, right? If you try to send on a different network, it won't be able to communicate.
That's how it's supposed to work. Thank you, Mr. Switch. And if you look back at our command prompt, you can see that we sent a ping message, and then we got a reply from Mark, from the IP address. Everything's good. Mark's alive. He's like, hey, yeah, Johnny, I'm here. And if we click on real time, it'll just complete it like it normally should. Bam, 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 really fast. Because these electrical signals are going really fast down these wires. But that's what's cool about the packet tracer. We can slow down time, bullet time, and watch it happen. Okay, we're about to go deeper. We're about to learn more about how this guy does things. Are you ready? Let's take a deeper look. The switch can do all this magic because it has a brain. A brain that can remember things like, hey, on my port FA02, that's where Johnny lives. And on my port FA01, that's where Mark lives. And the same thing goes for Denny and Lisa and anyone else who connects to the switch. He'll remember where they are. So when you send a message, he'll go, oh, well, I know exactly where Johnny is. He's over here, port FA02. He stores that information in something called the CAM table, which stands for Content Addressable Memory. Don't worry about that too much right now. We'll cover a lot of that later. Now, the switch doesn't know Johnny as Johnny. The switch knows Johnny as 00D097528936. That's how the switch knows Johnny, his layer 2 address. That's how the switch knows Mark. He doesn't know Mark's name, but he does know 00E0B0590897. Love that guy. What are these things? That's called a MAC address, often referred to as a layer 2 address. Every single device that you connect to the internet has a MAC address. Every one of them. Like, go ahead and look. Get your laptop out. Look for it. Like on this phone here that I would connect to the switch. Look, right here. There's my phone's MAC address right there. It's up.
Here it is.
It's often referred to as the burned-in address because this address should never change. That's how your device is identified. It's a unique identifier. So when I connect my phone to the switch and my phone tries to talk to somebody, boom, the switch learns, hey, that phone, which that phone's name is 9C57803844A, he lives on port 1. So if anybody wants to talk to him, it's going to be port 1. Now we'll cover more about layers here in a moment. I'm kind of building up to that. But this right here, doing this, and that wonderful, beautiful sound, yes, this is layer 1. Anything physical, the electrical wires, the metal wire that send electrical signals down to the switch, that's layer 1. So layer 1, electrical signals firing at light speed down an Ethernet cable, physical. And then we get to our switch, and now we're thinking about layer 2. And that's where our layer 2 address comes in. That's where the MAC address comes in. Layer 2 is often referred to as the data link layer, but we won't cover too much on that right now. I have to stop. I don't want to give you too much right now. Now you may be wondering, why isn't the switch just using the layer 3 address, like what we used when we pinged 10.1.1.2? Why doesn't the switch know Mark by that number? Well, the simple answer is that the switch can't even see that number. It has no idea what it is. You see, the switch is a layer 2 device and doesn't know anything about layer 3 or IP addresses or anything. That's why we're dealing with MAC addresses right now. Now watch this. Let's get back to our packet tracer. We're going to do a couple things here real quick. Let's click on simulation mode once more and let's open up Mark. We'll go to his desktop, go to his command prompt, and we're going to ping Lisa down here. So we'll do ping 10.1.1.5 and hit enter. The message was built. Now go ahead and click the forward message real quick. And I want you to click on this message right here we have. Click on it. Now, as you can see, we have 7 layers we're going to be talking about here very soon, but don't think about anything above layer 3 right now. Don't think about that. But notice this message we're sending to the switch. Notice what's not there. Layer 3 is missing. It's just layer 2, because that's all the switch understands. And also notice the to and from. So right here we have the from, which is the MAC address of Mark over here. And then the to is to Lisa's MAC address down here. And if we go ahead and step forward in time, boom, the switch receives it. If we click on that message again, we see that the switch receives it, and he knows exactly where to send it, because he remembers where Lisa is. And then if we click on that button, bam, it goes to Lisa. Now, I'm not sure if I want to show you this yet. Yeah, let's go ahead and do it. So click on that envelope right there. The message that just arrived to Lisa. You can see here that instead of just having layer 1 and layer 2, we now have layer 3 involved, because that's a layer that Mark and Lisa are talking on, layer 3. You see, we pinged from Mark's IP address 10.1.1.2 to Lisa's IP address of 10.1.1.5. And then Lisa's sending out a message, see, out to Mark at 10.1.1.2 from herself, 10.1.1.5. And then we step forward in time once more, boom, we see this message go to the switch. But then if we open that message, oh, layer 3's gone again. It's just layer 2, because that's all the switch cares about is layer 2. And that's how he knows where things are. That's where devices are, based on their MAC address. Now go ahead and click on real time, let that finish out. And we're going to jump into the switch's command line interface. And this might be your first Cisco command. Kind of exciting. So let's open it up. What we're going to do is we're going to look inside the switch's brain. So go and click on him and jump to the CLI tab. This is a whole new world for you. Yes, okay. Now hit enter, then type in enable and hit enter. Now you should have a hashtag sign right there next to your switch. Here's a command I want you to enter. Show MAC-address-table. We're looking inside the switch's brain and looking at his CAM table, where he keeps the MAC addresses and how they are assigned to the ports. Because Mark and Lisa just talked, the switch knows that Mark, which is referred to as blah 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 MAC address, lives at FA01, and then Lisa lives at FA03. And then if we go to Denny over here, and we go to desktop and command prompt, and we try to ping Johnny, 10.1.1.3, that's going to go through. It's being successful. Awesome. If we jump back into the switch and hit the up arrow to enter the same command, hit enter, well, now the switch knows where everyone is. He knows where Johnny is, where Denny is, where Mark and Lisa. He learned it, stored it in his brain, and now whenever someone sends a message, he goes, I know exactly where they are. Boom, right there. The hub just doesn't do that. And that's the job of the
Okay. Let's continue. Okay, so what was interesting there that you learned? Well, most things I already knew. Like, again, we can kind of, at a high level, explain it, I guess, if you want to. No, where are we? The switch, like, if you ask yourself, why not just send it layer 3? Because the switch has no idea what layer 3 even is. It just knows your media access control, which is stored in your CAM table, content addressable memory, which essentially the switch has. Do your devices have it too? Yes, actually. But it's more of a IP to MAC listing. So yeah. Yeah, so the switch interprets. So what is that again? Out in? Explain that. Out in is essentially what the packet is doing. If it's inbound, that means that like it's literally still receiving. Like it's what we receive. Like it would have our MAC address, and it would have or it would have our IP. And then outbound is essentially the destination, which again, that would have to, would it? Well, yeah, if you're using any type of IP service, I guess, or internet or sorry, web page or, wait, no, why not just use layer 2? Why not just use layer 2? Because, I mean, they're connected. I mean, I don't know. It's a silly question. How is it a silly question if you can't answer it? I mean, you can, I guess. Yeah. Almost all products used every day are built on IP. Exactly. And then the commands themselves, okay, I still remember them. Enable. I think most devices have some type of configuration startup mode like that. So enable is a good way. En, and then you can do show Mac -address -table. Is it?
The switch. We'll try to ping Johnny and hit enter. Well, now the switch
-address -table. Yeah. And what does that show again? Don't look. It lets you know, and how is that used often for troubleshooting? Like, it lets you know the MAC address to port mappings. Just like a MAC address is mapped to an IP for devices to communicate. Like, it has to know, like we use IP to communicate, but we identify at the MAC level, layer 2. And oftentimes, maybe you have to learn the actual thing somehow manually, or it's not dynamically learned, or the port has security on it and you're trying to do something that's not allowed, or it hasn't learned the MAC address for some reason. And you can verify that in the MAC address table, or yeah, something else.
switch knows where everyone is. He knows where Johnny is, where Denny is, where Mark and Lisa. He learned it, stored it in his brain, and now whenever someone sends a message, he goes, I know exactly where they are. Boom, right there. The hub just doesn't do that. And that's the job of the switch. He learns where everyone is by learning their MAC address, their burned-in address, and stores that in his brain, his CAM table, and marks where they are. So whenever he receives a message, he can forward those messages to the appropriate people, and not to anyone else that shouldn't hear about it. Now, when we're talking about layer 2, this message right here is referred to as a frame. All the messages going through the switch right here are frames. Boom, 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 frames just going around like crazy, because it's layer 2. When you think layer 2, think switch, think frames. Switch frames, layer 2. Switch frames, layer 2. Is it working? Is it going in there? But then when the message goes to Lisa, and we're talking about IP addresses in layer 3, do you know what it becomes? This message is now a packet. Now, just so you know, when you're talking to network engineers and other folks, they might refer to layer 2 messages, the frames, they might call those packets as well. We just get in the habit of it. If it's going across the network and it's going to people and it's a message, we often just refer to it as packet. It just happens. But technically, it's frames. Layer 2 frames, switch. Layer 2 frames, switch. Okay, now we're gonna talk a little bit about wireless. Here's a wireless access point, little baby Cisco one. Here's a bigger Cisco one. The reason I want to talk about them now along with switches is because they're basically doing the same job as a switch. But what's funny is they're more like a hub than a switch. They're kind of dumb. I mean, they're amazing, but they're kind of dumb like a hub. Let me show you. Looking back at Packet Tracer, if I scroll down just a little bit, you can see I have a little wireless network here. Let me add the IP addresses here real quick. Now, what I want you to do real quick is down here at the bottom, click on the lightning bolt. Very Harry Potter-esque. And then click on the lightning bolt again. This is a connection. It's like plugging an Ethernet cable, and we're gonna plug it into the access point here, and then plug it into our switch. We talked a little bit about wireless in the first video, but it's just an extension of the switch. So it connects to the switch with an Ethernet cable, and then it connects all the other devices via wireless, which we know to be airwaves or radio waves. So most of our devices, like our phones and everything else, connect to this access point, which is connected to a switch. Now, even though this access point is connected to a switch, he's actually more like a hub, and it's all about these connections right here. Let me show you real quick. I'm gonna have Mr. Denny here. I'm gonna click on Denny and launch his laptop. We're gonna go into his desktop and go to his command prompt, and we're going to ping, let's say, the first tablet down here, 10.1.1.11. So I'll do ping 10.1.1.11. Oh, and I forgot to go into simulation mode. Let's go into simulation mode down here, bring Denny back up, and boom. So as you can see, Denny's got his packet ready, and he sends this frame to the switch. Now, if we open up that frame, what do we see? Well, we see that the source is indeed Denny over here, based on his MAC address, and then the destination, well, what is that matching? Well, we scroll down here, we can see, yeah, it does match the first tablet here, based on his MAC address, and then we open up that frame, what do we see? Well, we see that the source is indeed Denny over here, based on his MAC address, and then the destination, well, what is that matching? Well, we scroll down here, we can see, yeah, it does match the first tablet here. So the switch knows that he lives on this port connected to the access point, but it's what the access point does with it that's so stupid, but it's just how wireless is right now. Let's skip forward in time. The access point has it now, but now
wait, I'm so confused.
we scroll down here. Here we can see, yeah, source is indeed, and he sends.
Yes, of course. The switch learns, or the source would be the port, and the port is associated with a MAC address. The switch doesn't send its own MAC address. That's silly.
This frame to the switch. Now, if we open up that frame, what do we see? Well, we see that the source is indeed Denny over here, based on his MAC address, and then the destination, well, what is that matching? Well, we scroll down here, we can see, yeah, it does match the first tablet here. So the Switch knows that he lives on this port connected to the access point. But it's what the access point does with it that's so stupid, but it's just how wireless is right now. Let's skip forward in time. The access point has it now, but now let's see what happens. Click next, boom. And once more, boom. Ugh. The message was sent to everyone like a hub. Now we'll cover wireless in more detail here later in this course, but just know for now, that's why people tell you plug into an Ethernet cable at all costs if you can, because a wireless connection is more like a hub. And the fact that all the messages are going to each device isn't the worst part. With hubs, it's just a traffic jam, collisions all the time, which is why switches are great. And we'll cover more on that later. But yeah, always prefer Ethernet cable, a hardline connection to a wireless connection if you can. Now, later versions of Wi-Fi, like Wi-Fi 6, do help out with this. I actually made a video on Wi-Fi 6 that you can check out up there. Then as we step forward in time, when the first tablet sends his reply back, the access point will then send it to the Switch, and then the Switch, like it's supposed to, will just send that to Denny. But then we had the same process happen again when Denny does send another ping. Hey, first tablet, are you there? The access point will still broadcast that out to everyone. All right, hope you have your coffee ready. Time for a quiz. Time to test your knowledge in what we just covered in this video. The questions I'm about to ask you are not easy. I pulled them from Boson XM, the best CCNA practice exam you can find. They are world renowned and they are sponsoring this video, so check out the link below for that exam. Anyways, let's see what you know. Question number 1.
Which of the following addresses will a Switch use to populate the CAN table? Source MAC address?
1. The bat, because we know we're talking about, makes sense. Destiny sends a frame. Set right? That's amazing. Select the best answer.
Which of the following addresses will a Switch use to make a forwarding decision? To make forwarding decisions. Destination MAC address?
Decisions, which 0 probably. However, it will use it video learning and weak tracing and watch packet switch port assignments. That's huge. SI model. That stuff. They have a non-NetSim. Pretty plain every. This is episode 2 of my free CCNA course. And a huge shout out to Boson Software, the official sponsor of this CCNA course. They are the reason this can be made available for free, so I highly encourage you to go check them out. They have the absolute best CCNA, CCNP, labs, and practice exams. This is a router. But what is it? Routers connect us to the internet. They also connect us to other networks. In this video, we're going to see why we need them and what they do in our networks and why I have so many of them. Holy junk sauce. And of course, we're going to be labbing. We're going to watch how a frame and then a packet will go across a network, access a web server, and then give us information back. This is how the internet works. You're going to learn that today. Let's get started. Oh, by the way, I'm giving away some Boson NetSim today on this video. Don't know what NetSim is? What's the best CCNA and CCNP labbing software in the business? If you're going for your CCNA or CCNP Enterprise or anything that you're doing Cisco, it's what you want. It's what you need. I'm giving away 5 copies of any of those products. Link below to enter the contest. Hurry up. It's going away soon. Johnny wants some coffee, and we're going to help him get it. Check this out. In our last video, we talked about this guy right here, a Switch. He's got multiple ports. You connect your computers to him, and they can talk. And that's exactly what's happening here. Johnny, Mark, Denny, and Lisa are all on the same network, and the Switch allows them to talk to each other. And in our last video, we explored how the Switch actually helps them talk. What goes on inside this thing. And it's pretty cool. But you see now Johnny, this is Johnny in real life. He's a Raspberry Pi. Johnny doesn't want to just talk to Lisa, Mark, and Denny. Johnny wants coffee. The coffee is actually way over here on a completely different network. And Johnny's over here. Not good, right? How does Johnny get coffee? And when I say Johnny wants coffee, of course he wants to go out to networkchuck.coffee and order some coffee. But this server, where this website lives, networkchuck.coffee, is on a different network. Here, the Switch can't help him. He needs help from somebody else. He needs a router. This guy right here. Oh, this guy. This is a Cisco 2911 router, one of my favorites. Oh, it's beautiful. Now routers come in all
You got something none of us.
Must have been brutal.
Oh, you don't even smile.
Thank you. I always knew
Must have been brutal.
Oh, you don't even smile.
Thank you. I always knew you were special. Loved.
You're not even close to baseline.
The real boy needs a real name. Joe.
Joe.
If anything happens to this, that's it. You're gone.
Like a real girl.
Little name.
Joe.
I love you.
You imagined it was you.
You look lonely. You look like a good Joe.
Dying for the right cause is the most human thing we can do.
You okay? Must have been brutal.
Oh, you don't even smile.
Thank you. I always knew
All shapes and sizes. This is just one type of Cisco router. This is a Ubiquiti router. Looks very different. And then typically your home routers look nothing like what I just showed you. A router is the perfect solution for this because a router's job is to connect networks. Let's put one on there. This is actually a virtual version of a 2911 router. Look, just like the one I showed you. How neat. So we'll put the router in between. And notice on a Cisco router, there's no ports on the front. They're all in the back. So let me turn that sucker around. Now plug Johnny's switch in to the router. And then I'll plug the coffee network into the router as well. Let's do that in virtual world. Bam, bam, and once more. Now before we keep going, I want to add, let's do that. Johnny's switch virtual world. Bam, bam, and once more. Now before we keep going, I want to ask you a question. Do we actually need this router? I mean, why can't we just do this?
Do we need this router? Yes. Why? Different networks. There's no layer 3 functionality otherwise. It's like trying to talk a different language between like a fucking, Asian guy and a fucking Arab guy. Like, you won't get anywhere. The message will be lost in translation.
Let's take away our connections, move this router out of the way, and then let's just connect our switches directly to each other. That should work, right? No, it won't. Here's why. I mean, we could connect these two switches and make them one giant switch, and that's essentially what would happen. But the reason these guys over here and then my coffee server over here are on different networks isn't because they're connected to two different switches. That's not it. It's because of these guys right here. Their IP addresses. We will go more in depth on this later because there's a lot more to it. But just know that when we talk about a network, we're normally referring to IP addresses and a group of IP addresses. So notice I have two groups of IP addresses here, 10.1.1.0 through 10.1.1.255. With my configuration, as long as you have an IP address in that range, you're on the same network. Now this right here, 23.227.38.0 through 23.227.38.255, that's a completely separate network. But you know what? Don't take my word for it. Let's actually try this. Let's see if it'll work. Let's go back to Packet Tracer. Now as a quick 30-second refresher on how a switch works, we'll have Johnny try to ping Mark over here, and then we'll have him try to ping my coffee server over here and see what happens. So I'll click on Johnny, wake him up. Come on, Johnny. Let me get this stuff out of the way. We'll go to his desktop. We'll go to his command prompt, and let's bring up a simulation real quick. So we'll click on the simulation button at the bottom right, so we can watch this stuff happen in bullet time. And I'm going to show you something that I did not show you on the last video, and that's how Johnny will learn Mark's MAC address. Now, why is it so important for Johnny to learn Mark's MAC address? Well, if you recall from our last video, the switch, the only language he speaks is layer 2. That's all he knows. MAC addresses is layer 2 address right here. Now, when Johnny pings Mark, he's going to be pinging his IP address. So his message, when he gets it ready, will be pinging 10.1.1.2. If Johnny were writing a letter, that's what he would put as the address. But if that's all Johnny had when he sent this message to the switch would be like, why is this envelope blank? I can't even see IP addresses. Who is this going to? That's what would happen. So Johnny must know the MAC address of Mark in order for the switch to know how to get it anywhere. But how? This is what happens. So from Johnny, I am going to ping Mark's IP address 10.1.1.2, and boom, let's watch what happens. All right, Johnny's got some envelopes. He's ready to send them out. These are frames right now. Notice we have a new message we're dealing with. It's called ARP, or Address Resolution Protocol. Essentially, it's a way that Johnny can find out what MAC address is tied to 10.1.1.2, because he has to know that to be able to send it to Mark. Let's open that up and see what's inside. Let's click on that. And again, we're dealing with layer 2 MAC addresses, but also notice down here, we have some information about this ARP packet. Like for example, the source IP is Johnny's source IP 10.1.1.3, and then the destination IP right here, 10.1.1.2, that's the missing MAC address. He's trying to find out Mark's MAC address. And then of course, because this is a layer 2 frame, we're talking about MAC addresses, so the source MAC address that the switch will use is Johnny's MAC address. But then look at the destination. What the junk is that? FFFFFF. This
What the cast address? Or broadcast.
is what's called a broadcast address. It's the layer 2 switch equivalent of someone going, who belongs to 10.1.1.2? When he sends it to that MAC address, it's going to go out to everybody. Watch what happens. We'll click next. It goes to the switch. Let's open up that packet and take a look. Or frame, I'm sorry. See, it happens. And look at this. This is so cool. So over here, the switch receives it, and then it's about to send it out. And notice it's going to go out all these ports on layer 1, which remember, layer 1's the physical. It's these. I just unplugged something. Oh, the sound. It's all the physical stuff. So let's click next, and boom. ARP messages going everywhere. And what will happen is Lisa will go, oh, I'm not 10.1.1.2, and neither am I, says Denny. But Mark, yeah, Mark is 10.1.1.2. So he says, hey, that's me. I'm your guy. I'm over here, Johnny. So we'll step forward in time. Mark is the only one who responds, saying, yes, that is me. So he'll send, and then the switch sends that to Johnny. So Johnny now knows Mark's MAC address. So we can send him a ping. If I open that frame up that's sent to the switch, we see the source is Johnny's MAC address, and the destination is Mark's MAC address. And if we click continue, it'll go to Mark. Mark will respond. Bam. Johnny gets it. If we check our terminal real quick, our command prompt, it's happening. And if you click real time, it will just continue. So that's what happens when someone's on the same network. Johnny knows that Mark is on the same IP network. But what happens when Johnny tries to get to the Network Chuck Coffee Company? Let's see. Let's have him ping it. So we'll open up Johnny once more here. Go to his command prompt, and we'll ping the IP address of my coffee server. So ping 23.227.38.65. Let's go to our simulation so we can watch this in real time. And let's hit enter. Boom. Okay, so far so good. We have an ARP frame that Johnny's getting ready to find out where my coffee server lives, maybe his MAC address. Let's open it up and see. Click on that message. And, do you notice anything weird here? You know what? Pause the video right now and see if you notice anything that might be strange. Pause. Okay, here we go. So just like before, Johnny's sending a frame to a broadcast address to say, hey, who's got this IP address? But he's not asking about the IP address of my coffee server. No, look here. This is the source IP. This is his IP address. But he's trying to discover the IP address, or the MAC address rather, of 10.1.1.1. Why? Because when he tried to find out Mark's MAC address, this right here was 10.1.1.2. That was the destination. Why is this different? Because Johnny knows. Johnny knows the coffee server is not on his network. So he's not even going to try to connect to that coffee server on layer 2. He's not going to try to discover his MAC address. He gives up immediately. Watch what happens. Let's step forward in time. So Johnny sends this ARP message saying, anyone out there, are you 10.1.1.1? And the switch will send this out. And as we step forward in time, stepping forward, no one responds. Johnny keeps sending out ARP requests. Does anybody have 10.1.1.1? Does anybody have it? And no one responds. Who is 10.1.1.1? And why is Johnny trying to talk to him? Let's find out. It comes down to how we configure Johnny. Let's open up Johnny real quick. Go to his config. And the answer is right here. There it is. 10.1.1.1 is his gateway. Gateway is another word in the networking world we use for router. As I said before, Johnny knows that people in his network are 10.1.1.0 through 10.1.1.255. Johnny knows that if anyone has an IP address in that range, they're in his network, they're in his neighborhood, he can just walk over and talk to them, find out where they are. Like, yeah, I know Bill. He just lives 2 doors down. I can walk over there and talk to him. But if Johnny tries to reach an IP address outside that range, he knows it's not in his network, and he's going to need some help. He needs help connecting to a different network, and that's where a router comes in. So let's throw the router back in there and have some fun. This is going to be so cool. Watch this. Now, before we move on, it's important for you to know that I did pre-configure this router. Not a crazy amount of configuration, but I did add some configuration to make this work. For the most part, switches work out of the box, no problem. A router is a bit more complicated because it has to know how to route between networks. He's a router. He has the map of how to get to things. I'll show you what I mean. Check this out. We're going to have Johnny here once again try to ping networkchuck.coffee. Let's open up his command prompt. So I'll go to his command prompt. We'll go back to our simulation. We're in simulation mode, bullet time mode, and let's watch some crazy router magic happen. So we're gonna ping the coffee server and go. Now, same story as before. Johnny knows that this is not on his network. He knows that Bob lives in another state, and he can't just walk over there. He's like, I gotta use my gateway. I gotta find my router, and his router will be connected to his network. Watch what happens. Let's step forward in time. The ARP message is sent out to the broadcast, and keep in mind the same reason that Johnny's sending an ARP packet for the router is the same reason he had to send one for Mark. He doesn't know the MAC address for 10.1.1.1, and he must know the MAC address so the switch will know how to get his stuff to the router. The switch sends it out to everyone, and Lisa, Denny, Mark, this server right here, which I'll talk about here in a moment, they're all like, yeah, that's not me. But then the router's like, that's me. I'm 10.1.1.1. And he sends a reply back saying, yep, that is me. The switch tells Johnny, hey, this guy lives here. That's his address. Walk on over. So Johnny does. If we open up that frame that just arrived at the switch, we can see the source is indeed Johnny, and the destination is the router. And then we'll step forward in time. It arrives at the router, and then we have something blinking and flashing. Let me zoom in on that. This is so cool. What's happening right here? Let's open up the freaking out guy right now. Isn't networking fun? Oh my gosh. Okay, here's what's happening. Now, what did the router receive right here? Well, if you just look at layer 1 and layer 2, we know that he received this frame on his gigabit 00 interface, as this little message says right here. But because we have layer 3 involved, we know that to be called a packet, remember? That's what routers do, man. They are all about layer 3. This little message says right here. But because we have layer 3 involved, we know that to be called a packet, remember? That's what routers do, man. They are all about layer 3. They are layer 3 devices. They can handle the IP addresses. That's the language they speak. So this is what the router received. Notice it's from the MAC address that belongs to Johnny right here, and it's to his interface. But then look what he's sending out. And notice what's missing. Layer 2. Now, according to his layer 3 map, he knows that 223.227.38.65 is that way. But that's layer 3. He doesn't know where he lives at layer 2, and because he's about to send this frame to the switch, he doesn't know how to tell the switch how to get to him, and that's important. And that's the reason we have this freak out message, like, I don't know what his layer 2 address is. So how does the router find out? Well, how did Johnny find out? An ARP message. He says, hey, where is 23. Blah, 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 and he broadcasts that out. Watch. Right next to the freak out message, we have the ARP message right here. From the router to the broadcast, and we're looking for anyone that has this IP address. Anybody got this? Anybody out there? And let's step forward in time and watch this happen. So he sends the ARP message to the switch broadcasts it out, and because the server is the only one that is on the network, he receives it. The server's like, hey, that's my name, that's me, I'm over here. So he sends the response to the switch. The switch is like, yeah, I know where this guy is. Hey, router, I found him. And now that everyone knows where everyone is, Johnny's ready to send his message. So we've opened up Johnny's message over here. I want you to pick up on this. In the layer 3 header, Johnny has his IP address as the source, the coffee server as the destination. But on the layer 2 level, we have his MAC address as the source, and then the destination is the MAC address of the router. So layer 3 right here is directions for the router, saying, hey router, this is where I want my message to go. And then layer 2 right here is directions for the switch, saying, hey switch, this is where I want my frame to go. It's gonna go to the router, and the router will take care of the rest. Let's watch it happen. Step forward in time. The switch receives it. If we open that message up, we can see it's only layer 2, because the switch can only see layer 2. It's going straight to the router, so we sent it to the router. This is so cool, isn't it? It's amazing. Let's open up that router's message and look at that. This is the message he received. So layer 2, it's from Mark's MAC address to his MAC address. Layer 3, it's from Mark's IP address to networkchuck.coffee's IP address. And now for the outbound message, because he learned where the coffee server's MAC address is, he can send it out. So here's the layer 3. And if the switch, he's got the directions right here. From his MAC address to the coffee server's MAC address, which ended in 1AC7. If you look at that, yep, it matches up right there. Let's watch it happen. Boom. The switch sends it out. And the coffee server got it. And then the coffee server replies and sends it back. The router sends it through. The switch gets it. And then Johnny gets it. Isn't that amazing? And this happens millions of times every day across networks across the world. Isn't that just crazy? Now, I want to show you one more thing. It's kind of a sneak preview to what we're going to be talking about later. But obviously, Johnny, he wants to order some coffee from networkchuck.coffee. But you can't order coffee by just pinging the web server. You have to visit the website. And we can do that. Let's have Johnny do that right now. So I'm going to reset everything and we'll get this thing ready. This is going to be amazing. Don't let this overwhelm you. We will go over the details of how this works later on. But I just want to show you because it's so neat. I can't help myself. So we're still in simulation mode. Let's open up Johnny real quick. And instead of going to the command prompt, we can go to his web browser. So I'll click on web browser right there. And the website is networkchuck.coffee. Now the main difference here is that we're not using an IP address, at least to start with. It's this friendly name that we normally use, like facebook.com, youtube.com. But how does that work? We know the switch loves MAC addresses, and that's what he talks. That's the language he talks, layer 2. The router loves layer 3, IP addresses. Who deals with names like this? Well, the short answer is no one. Johnny must know the IP address. Or rather, Johnny's computer must know the IP address. So when he types this networkchuck.coffee URL in, there's got to be some way that his computer can find out what the real IP address is, which we just pinged moments earlier. That's called DNS, and that's what our DNS server here is for. Let's watch it happen. I'll click go, and boom. Oh, whoops, I forgot to configure the DNS server. If I go to config, under his default gateway, we have DNS server, which stands for domain name service. And I'll put in the IP address of our DNS server up there, 10.1.1.50. This guy right here. So let's go back to our web browser and try it again. Go. And here we go all over again. We have another ART packet because Johnny needs to get the information on networkchuck.coffee. He needs to learn the IP address, and he knows that this server, the DNS server, knows that information. That's 10.1.1.50. And that's his first job. So he has to go through the process again of learning the MAC address of the DNS server. Let's walk through that now. Stepping forward in time. Sends an ART message. The switch will broadcast that to everyone. The DNS server responds because that's his IP address. And he's like, here's my MAC address. That's me. The switch sends that to Johnny. And Johnny's like, yes. So now Johnny can send his DNS query to find out where networkchuck.coffee is. What's the IP address? So he'll get that message ready. So he sends it out. It goes to the DNS server. We'll take a quick little peek inside that real quick. We'll open that up. And a lot of stuff going on there. That's the other layers we'll talk about. Don't worry about that. But essentially the server's like, yeah, I know where that is. Here you go, Johnny. Here's the information. So he sends it to the switch. The switch sends it to Johnny. Johnny learns where this is. Now let's open it up real quick. I'll show you. Let's open that up. And we'll go to the inbound PDU details. Again, don't worry about that just yet. We'll scroll down all the way to the bottom. We can see that the information, the DNS answer is right here. The name, networkchuck.coffee, and then here's the response, the IP address of our server. So we'll step forward in time. Johnny will send his HTTP GET request. We'll cover more on that later. To the router, to the switch. Now what you might be noticing is that we didn't go through the whole process of learning the MAC address of the router, and the router learned the MAC address of the coffee server. No, it remembered. It puts that in its cache, and it stores it. So we don't have to do it all over again. Now I will eventually forget that information so it can relearn it. But again, more on that later. So let's step forward in time. It goes to the server. The server gets it, responds back, and you know what? I'm going to switch to real time. Let's open up our web page, and there it is. You need to drink coffee right now. And there's our website. As you can tell, it's been expertly designed. And by the way, that's real. If you want to buy my coffee, networkchuck.coffee, it's delicious. It's what I'm drinking right now. It's real. Now, I've got this lab in a link below. If you didn't follow along with me throughout the right now, it's real. Now, I've got this lab in a link below. If you didn't follow along with me throughout this, go ahead and open it now and try it for yourself. It's really cool to walk through all this and just see it happen. Like, this is how the internet works. This is what happens when you get on your computer and you go to youtube.com. This process happens. This right here is your home router. You're Johnny. Now, the real internet isn't this simple, right? The real internet is going to be like this router connected to another router, connected to another router, connected to another router, and then eventually getting to my coffee website, as we covered in the first video. But the process is still the same. The router is connecting these two separate networks. And remember, when I say network, I'm referring to the IP addresses, layer 3. These guys over here have a different group of IP addresses than these guys over here. Your home network will be a different group of IP addresses from the rest of the world. And that's why you need a router to connect to the internet. And inside of this router's brain, if you pop him open, he has a map to other networks and to the internet. Like, let's take a look. Let's have you enter another Cisco CLI command right now. Let's pop it open. Let's do this. I'm going to click on the router. We'll jump on over to his CLI tab. We'll hit enter and then type in enable. To see his map of IP addresses and where to reach different networks, we'll do show IP route. This is a command that network engineers use all the time. You're already doing networking right now. Let's hit enter and boom. I'm going to expand this out a little bit here. And this might look a little overwhelming, but here's all it's saying. The group of IP addresses that Johnny belongs to is right here. 10.1.1.0/24. That's just a shorthand way referring to 10.1.1.0 through 255. And in the router's map, he knows that it's actually directly connected to his interface, gigabit Ethernet 1, or I'm sorry, 00. And the same goes for my coffee network over here. There's the network, and again, it's a shorthand way of saying 23.227.38.0 through 255. And that's actually directly connected to gigabit 01. So when Johnny said, hey, I want some coffee, I want to order it right now, and 55. Coffee network over here. There's the network, and again, it's a shorthand way of saying 23.227.38.0 through 255. And that's actually directly connected to gigabit 01. So when Johnny said, hey, I want some coffee, I want to order it right now, and he sent his packet to the router saying, here it is, I want to go to this guy, the router's like, oh, well, let me check my map. Oh, there it is. There's the network. It's actually connected to my gigabit 01 interface. I'm going to send it out that interface. That's how the router knew. Now, this is very simplistic routing. Routing gets crazy. Like if you were to look at a router on the internet, let me show you real quick. This is actually one of the routers on the internet. Check this out. I'll enter the command show BGP, which is a routing protocol. We'll learn more about those later. IPv4, unicast. Let's see what we got. And all of these are routes to different networks on the internet. Like, I can keep going. I mean, look at this. This is insane. This is this router's map. This router is probably huge, very expensive router. But this is an example of A, how big the internet is, and B, what a router can do, why it's so powerful. All right, we'll never reach the end of this. I'm just gonna stop. And that was episode 2. Now I changed it from days to episodes. Makes more sense for me. If you have any comments or questions,
Okay, so explain everything that was discussed here and things that kind of were not very clear to you. Okay. So every device communicates at layer 2. like the direct connections, right? So layer 2. But this connection from this network to this network is always layer 3. Okay, so what does that mean? That means that you have to remember that. Let me first. That when you, like, let's say you try to reach the server, what happens? Well, first we say, oh, we'll do like ping, and you put the IP here, ping XIP. Okay, what happens? Your device is not dumb. A computer is not dumb, so it does some logic. It sees, is this IP on the same network? And how does it know that? Is subnetting. So this is like, that would be /24. You know, each, this is 8. This is essentially like 8 binary digits. 3, 4, 5, 1, 2, 3, 4, 5, 6, 7, 8. That's one of these. 255. That's just like the size of IP potential. This is the subnet. Okay, so in this case, how do you know it's a different subnet? Well, you already know if the first number is different, and it's just not going to be the same subnet at all. If this was 10, there's a possibility that it had a 255 subnet, but in this case it's not. So okay, so what does it do? It then uses its default gateway. You have to set up a default gateway. Usually this is already set up. Every device needs to know how to reach other networks, and it knows that by its default gateway. Every device. If you want routing functionality, which means connectivity between networks. Okay, so what does it do? It tries to reach its default gateway. Okay, at what? At layer 2. So what if it doesn't know its MAC address yet? That's the thing. That's where ARP comes in. ARP, any device that's directly connected uses ARP and MAC addresses, or MAC addresses as its communication. I like the analogy, it's like MAC address or layer 2 communication is like normal talking or even whispering. You're so close to someone. Routing is a lot of extra work. We're using IP addresses, and it's essentially like shouting across the room to reach someone else. But the other person won't hear you if you don't do it at layer 3, because this is unique across networks, right? Like it depends, like across, like inside of a network. So this is one network, right? Like at the end of the day, this is a network. If you want these people to communicate, you cannot have them have the same IP, because, I mean, it would just be confused. It wouldn't know where to send. It would send to the quickest or nearby people, I think. But anyway, so it reaches ARP. So what does that mean? It asks, what's the MAC address of this IP, which is default gateway. So what would happen? It would send, switch would say, well, I know it's, well, no, sorry, because it would be a broadcast. Broadcast is every device. So it's go on all of them except the incoming part. Router would receive it. Essentially, there is the input or encapsulation part and then the encapsulation. So the input field would be, or destination, I guess. I don't know how to explain it. The input right now, it would still be encapsulated, right, with the previous information, and it would say this is this IP, and then what's your MAC address. Router would say, yes, I have this IP and this is me, so I will send you your MAC address. Johnny would fill its content addressable memory table in its cache. The implication is eventually he will forget it and we'll have to redo this ARP process.
In an institution.
and it learns it. So now it knows the MAC address to use to request, and boom, it does that. Let's clear this up a bit. And yeah. And then nowadays these can communicate at layer 2. You have a layer 2 connection. Because again, this is the same network. Is it? Well, no, that's not really accurate. What do you mean? Well, funnily enough, the connection to the gateway is one network. Is it? Yeah, because it's a /32. Like, it's a single connection. And everyone has this kind of singular connection to the gateway, I'm pretty sure. It is one network. And if you did show IP route, you'd be able to see that. By the way, these routing tables, when they're part of like internet routers, there's like fucking millions of entries. So it's totally why. How? Because think about it. You have millions of ways to reach something, right? Like you have Google, you have YouTube, you have like friends' public IP that like you play games with. You have, of course, it's sent all to the default gateway for you. Yeah, your default gateway would be your ISP.
And now that everyone knows where everyone is, Johnny's ready to send his message. So we've opened up Johnny's message over here. I want you to pick up on this. In the layer 3 header, Johnny has his IP address as the source, the coffee server as the destination. But on the layer 2 level, we have his MAC address as the source, and then the destination is the MAC address of the router. So layer 3 right here is directions for the router, saying, hey router, this is where I want my message to go. And then layer 2 right here is directions for the switch, saying, hey switch, this is where I want my frame to go. It's gonna go to the router, and the router will take care of the rest. Let's watch it happen. Step forward in time. The switch receives it. If we open that message up, we can see it's only layer 2 because the switch can only see layer 2. It's going straight to the router, so we send it to the router. Receives it. If we open that message up, we can see it's only layer 2 because the switch can only see layer 2. It's going straight to the router, so we sent it to the router. This is so cool, isn't it? It's amazing. Let's open up that router's message and look at that. This is the message he received. So layer 2, it's from Mark's MAC address to his MAC address. Layer 3, it's from Mark's IP address to networkchuck.coffee's IP address. And now for the outbound message, because he learned where the coffee server's MAC address is, he can send it out. So here's the layer 3, and if the switch, he's got the directions right here. From his MAC address to the coffee server's MAC address, which ended in 1AC7. If you look at that, yep, it matches up right there. Let's watch it happen. Boom. The switch sends it out, and the coffee server got it. And then the coffee server replies and sends it back. The router sends it through, the switch gets it, and then Johnny gets it. Isn't that amazing? And this happens millions of times every day across networks across the world. Isn't that just crazy? Now I want to show you one more thing. It's kind of a sneak preview to what we're going to be talking about later. But obviously, Johnny, he wants to order some coffee from networkchuck.coffee, but you can't order coffee just by just pinging the web server. You have to visit the website, and we can do that. Let's have Johnny do that right now. So I'm going to reset everything, and we'll get this thing ready. This is going to be amazing. Don't let this overwhelm you. We will go over the details of how this works later on, but I just want to show you because it's so neat. I can't help myself. So we're still in simulation mode. Let's open up Johnny real quick. And instead of going to the command prompt, we can go to his web browser. So I'll click on web browser right there. And the website is networkchuck.com. This is episode 3 of my free CCNA course. And a huge shout out to Boson Software, the official sponsor of this CCNA course. They are the reason this can be made available for free, so I highly encourage you to go check them out. They have the absolute best CCNA, CCNP, labs, and practice exams. Okay, I need you to stop and think about this for a second. I want you to appreciate the fact that this device right here, a Raspberry Pi, can connect to a network and talk to my iPhone. They can share photos, they can email each other, do whatever. It might not seem amazing because this kind of stuff is just commonplace. It's what we're used to every day. But once upon a time, a long time ago in a galaxy far, far away, if you had a device that was made by 2 different companies, they could not talk. This is where things like the TCP IP model or the OSI model, networking models, save the day, like for real. But how? Let's take a look back in history real quick. A long time ago, I'm talking Stone Ages, 1960s. Some smart guys are sitting around with their computers and they're thinking, man, gee willikers, I really wish they could talk to each other. I wish I could share a file with you, friend. But they couldn't. But then they hatched an idea. They came up with something. They go, what if we can network these things together? What if we can connect our computers together and we could send data across? They did that. 1969, the birth of the first network. We called this, or they called this, ARPANET. The US DoD, or the Department of Defense, came up with it. And it was revolutionary. Like, people could actually have their computers talk to each other, which I know sounds like not a big deal right now, but back then, that was it. That was the new thing. But hold on, here's the problem though. This was more of an idea. Like they legit did it. Like here's the first like network diagram I think there ever was. Check this out. Look at that thing. I have no idea what's happening. And when I say idea, they were like, yeah, this is a cool thing we can do. They actually invented what's called packet switching, which is what we do today. But what they didn't have yet is the how. How do we make these computers talk to each other? You see, that part wasn't quite ironed out. But the idea spread like wildfire. So companies like IBM, they were like, heck yeah, we have computers. Let's design our own network. And they did. It was proprietary, meaning it only worked with their stuff, which is fine if you have an IBM computer, but there wasn't just IBM. There were other companies, and guess what these other companies did? They also designed their own networks. Now, sorry, let me step back. When I say design, I mean they like invented their own networks. They came up with the idea of how to actually connect computers together. And because these networks were proprietary, they couldn't really play well with others, meaning these networks could not communicate. You couldn't have this device talk with this device. They were basically speaking different languages. This network over here is like bonjour, and this network over here was like, what? No idea. Now I want to hammer this home because this is some primitive stuff. I'm talking like this is before Ethernet cables were invented. Like we're so used to Ethernet cables. We're so used to the Ethernet ports. These weren't a thing. Each of these companies had different versions of whatever they called theirs. Like you ever try to charge your iPhone with an Android charging cable? It doesn't work. It's just not compatible. That was the networks of yesteryear or a long time ago. Now eventually they realized, hey, this is kind of stupid. Maybe we should all use the same networking stuff. Yeah, let's do that. Now, easier said than done. This involved meetings and committees and I want to do this, I want to do that. You're wrong, sir. A lot of that kind of stuff. Now, there's a long and maybe interesting history if you're into that of how this all came about, but we eventually ended up with a networking model. A model that defines how we can connect our stuff. So that when IBM makes a computer, when Apple makes a computer, when Microsoft makes a computer, we're all putting the same technology inside that computer to make it talk to the other computers. That's why it's such a beautiful thing that a Microsoft computer can send a photo to an Apple computer. We're all using the same networking technology. We're using the same networking standards. Now, actually, honestly, we ended up with two models. One that we actually use and then one that we still cling on to and talk about all the time. I'll show you. The model we use today is called TCP/IP. This is what every computer supports and has implemented into their system. The TCP/IP model, and they also call it the TCP/IP stack. Now the other model, he wanted to be the one that won so badly. People were on his side, they were campaigning, but he just did not win. TCP/IP won for a variety of reasons, but it's just more widely adopted. So then why am I still talking about him if TCP/IP won? I'll show you. It's weird. Now again, TCP/IP is just a list of rules or guidelines, standards on how computers can communicate, how we design those systems. And there's a lot that goes into that. So to make things more simple, more digestible, easier to understand and implement, we divided all those functions into layers. Layers like this right here. Each of these layers defines some kind of protocol or standard we'll use when computers connect. So for example, the physical layer, we know it's going to involve Ethernet cables. The network layer, all about IP addresses and routers. So with this standard, we all agree we're going to use IP addresses when we communicate over the internet. Before that standard, that wasn't really the rule. You could have done anything. You could have used names from Star Wars or something. I don't know. Transport, we got TCP, UDP, port numbers. We'll talk more about that later. And then application, like, hey, when I open up my web browser and I go to netflix.com, what protocol am I going to use? Do we all agree to use the same protocol? We all agree to use the same stuff, and it's beautiful. Now we can all talk together. We can all network together. Now this is the traditional view of the TCP/IP model, the layers we see here. If you're studying for the CCNA, the 200-301, you might see the physical layer divided into two separate layers like this, which I happen to love. And if you watch my last two videos in the series, you're already familiar with the first three layers here. You've already seen them in action going through a network. We got our physical, the Ethernet cables, the network cards, the electricity flying. That's our layer 1. And then we talked about our data link layer. This is where our MAC addresses come in. Our layer 2 addresses, how hosts on the same network can communicate. And the switch uses those layer 2 addresses, those MAC addresses, to know where to send information. And then of course we have our layer 3, our network layer. We know this to be IP addresses. We know that we assign our devices IP addresses, and this is how they communicate. This is how the router can know where to find people and route those packets to the right people. And then we have our other layers, and we will talk about those, but not right now. We'll get to it. Okay, now, what about the OSI model? Where does this guy come in? Well, let me show you. Similar to TCP/IP, he works on layers. In fact, he shares the same layers as the TCP/IP model. He just has a few extra. So physical data link and network transport. Yeah, well, let's talk. That's the same.
Do you still remember? Yeah. Physical data link network transport. Application is layer 7, so we're missing 2 layers. There's presentation and secure
Let me scoot this guy up a bit.
session.
There we go. Now, as you're studying networking, as a network engineer, the main difference between the TCP/IP model and the OSI model are these 2 extra layers. Now, the concept of these layers, what they bring to the table, do not go away with the TCP/IP model. I'm saying it too much. All that happened is we stuffed those 2 layers inside the application layer. But Chuck, you still haven't told us why we're talking about the OSI model. Why are we even talking about it? This is why. I told you these 2 models were at war with each other. Who was going to win? And during those wars, it was widely believed that the OSI model was going to be the one that was adopted, which by the way stands for Open Systems Interconnect. And because it was thought to be the clear winner, we started using the layers that the OSI model has as our day-to-day terminology. And even when TCP/IP was the clear winner and it killed and murdered OSI, we still refer to the OSI layers when we describe network functions. Now again, not a huge deal because layer 1, 2, 3, and 4 are the stinking same as the TCP/IP model, as long as you're referring to the Cisco version of it right now. But when you get up to the layer 5, layer 6, and layer 7, clearly we got a little disconnect there. But when network engineers talk about it, OSI always wins. We will always refer to the application layer as layer 7. This right here is layer 7, and there's only 5 layers here. This is how we do it. It's how we roll. But I will say this. If you're trying to learn networking, if you're studying for the CCNA, you need to know both of these models. There's a fun way to memorize this. So the OSI model, 7 layers, hard to memorize. We'll use a mnemonic device. So application, presentation, session, transport, network, data link, physical. Let's try all people seem to need data processing. I'm sure there are better ones. That's just how I learned it. Let me know below if you have a better one. I can't tell you how many times throughout my career I've referred to that phrase, that mnemonic device, to remember the 7 layers. And then what about reverse? What if you're not going from application to physical? What if you're going from physical to application? Which can happen routinely, right? I got one for that too. Please do not throw sausage pizza away. Makes me hungry every time. Now again, a big reason to remember and memorize the OSI model is A, you need to know it for any exam you might be studying for, and B, it's honestly the thing we reference the most when network engineers are troubleshooting or working through any kind of networking issue. Oh, that's a layer 7 issue. Application. Hands off, not my problem. Or hey, that's a layer 1, layer 2, layer 3, or layer 4 issue. Okay, time to see what you learned. Get your coffee ready, your thinking cap on. Let's do this. Exam questions right now. Question number 1. Which of
the following operates primarily at layer 2 of the OSI model? Select the best answer. Beta link. Or a switch.
the following operates primarily as switch? You're absolutely right. If I hit show answer, fingers crossed. Yes, I'm right. The switch operates at the data link layer, layer 2 of the OSI model. Router? Nuh-uh. Where's the router operate at? Layer 3, IP. Where do they do is just repeat a little. They also store what primarily are the answers. The physical layer of the...
Which of the following devices operates primarily at the physical layer of the OSI model? Select 2 choices. I'm not even looking, I'm just trying to predict the answers. Hub. Repeater. Huh?
The OSI talked about Bridget and repeat. A ton of guys in David Bombal and I run. Go check it out. It's pretty cool. And also, in just a few hours, I'm launching episode 4 of this series, where I dive deeper into...
So, what was interesting to you there? Well, I'm going to kind of speed around this playlist a little bit because I already know most of this shit. I don't want to spend too long on it. Like, genuinely, not just saying that as a way to get by quickly, but it seems like I haven't forgotten that much. In the lab, I'm guessing yes. I'll get to the lab as soon as I finish this playlist and get a good lab playlist. I think this is more efficient. But yeah. Okay, so I think, like, if you often you ask why, I would say why TCP? Why computers are a bit like humans, that they have languages that they need to operate, to do things. Okay. Now, like, this is, I kind of like this. There was ARPA, I think it's called. There was IBM. They all had these like implementations of networking communications. So so it's software at the end of the day. Don't forget that. When you say firmware, no. The OSI or TCP/IP, again, what do they? This is just it's a model that tries to explain how computers operate and how it's standardized across devices. Across operating systems, actually, because the software lives on the operating system, I suppose. Okay, so what else? But we needed a way to standardize such that, you know, it's not like someone speaking Chinese and Spanish, but rather it's 2 people speaking English or something, such that we could communicate and know what to expect. What to expect? What do you mean? Because the packets are the language that we transport across networks, and the packets need to have some type of predictable data, such that the computer can say, "This is the next field I suspect. This is the next field I suspect. This is the next field I suspect," and that way it can continue what it's doing. Okay. What else? What else? Explain the layers again, an easy way to memorize, and maybe the meaning behind each layer just shortly, in a way that's like you're teaching a fucking 6-year-old. A 6-year-old? Okay. So you have 2 model. What is model? Like, you have 2 ways to represent how computers, how chips speak with each other, right? Because, I mean, what is the most basic form of a network? 2 computers connected via a crossover Ethernet cable, which is how the first people actually did it. It's the most basic network. It's called what? A peer-to-peer connection. Now, peer-to-peer networks now exist, but at much greater scale and much more complexity, as opposed to just 2 computers connected via Ethernet crossover cable. But yes, it is a way that we can understand how computers talk with each other. And you have the OSI model, okay, the OSI way that we view how computers talk, has 7 layers. Now those 7 layers, again, this is like the reason I like to really encode this like a fucking, knowing that a fucking banana is yellow, second nature as you can make it, is because it is literally the best model to just understand at a high level how things work. And this is why it was created, so people could understand it as well and know what developers need to know about, you don't need to fucking know every detail, but you can understand how a computer then operates, from physical to data link to network to transport to session to presentation and to application. Those are the 7 layers, okay? So what does that mean? That means that when you grab your phone, the average Gen Alpha or whatever, you open your phone, right? And the minute you open your phone, actually, you're already connected to the internet, right? You're doing stuff. Often, let's make it simple. You open Instagram, the page loads up. You open the web app of Instagram on your laptop, the page loads up. What you're doing there is a HTTP GET request first. Now, wait, so you start layer 7? Well, yes. Like, you're using, like, we're talking about what you do, right? You're on the web app. We're talking from the human POV. Like, of course you could say, well, how do you, like, yeah, things are happening bits at the layer 1 already. Yes, of course. But you open the web app, you design a HTTP GET request. That's your application layer. You're interacting, you're doing stuff with the application. Then you present that data in a way, you encode it. Now, I think also actually anything JSON, any encoding format, security even is considered here, but then transport, that's presentation, SSL, TLS, yes. TLS is more common than, is it? Or is it the opposite? Wait. TLS is more common than SSL, I think, right? TLS, okay, it's a modern version, transport layer security. Then you essentially have, again, like, it is the packet itself, which is how we consider and view. There's many ways to view it, but it's application at the top, presentation, session, transport. Now, actually, are you saying a packet has each of these fields? It has a protocol usually for each, yes. So there's 7 fields? I don't know, but so TLS, TCP, then transport, then IP. How do we know the IP of what we need to reach? Good question. DNS, domain name service. You obviously, like, imagine you had to work with IPs. People just had to work with them. Like, holy fuck, that would be painful. So we don't do that. So we have host names, human readable names that your DNS server resolves. Usually, I think that's just your ISP has a server there. So how do you communicate with that? Well, first you talk to your router, your default gateway. Your default gateway has to be set up as an IP. Usually that's already done by default. How so? Because you're all-in-one device that you have in your local area network, which is all-in-one. What does that usually mean for most homes? A router, small switch functionality, a phone connection, a WAN connection, obviously, which is like even a modem, I think. No, that's not really true. No. Modem is separate. Modem is separate for sure. By the way, modem, remember that, like, every network has a modem. Like, if you have fiber, you still need a modem to modulate and demodulate the light signals to electrical signals. Which, by the way, What are the most common modulation schemes inside of a network? Yes, Wi-Fi. QAM is one. QAM. This is where I'm a bit lost.
OSI model and the TCP/IP model. We'll actually watch a packet go through a network and we'll analyze each layer as we hit it. So be looking for that. It already might be up actually, so check it out. Well, anyways, episode 3, that's a wrap. I'll catch you guys later. This is episode 4 of my free CCNA course. And a huge shout out to Boson Software, the official sponsor of this CCNA course. They are the reason this can be made available for free, so I highly encourage you to go check them out. They have the absolute best CCNA, CCNP, labs, and practice exams. TCP/IP and OSI, networking models that define how we connect our computers. Without these, we wouldn't have networking. So in this video, we're going to watch it happen. We're going to follow a packet as it goes through a network and how it interacts with each layer. Let's do it. Okay, same scenario as the last video. Johnny wants some delicious Network Chuck coffee. So he needs to go over the internet to access networkchuck.coffee to order some coffee. Let's watch his packets go across the network, and we'll analyze the layers as it goes across the network.
By the way, about packet, like a layer 2 at layer, like, it doesn't, like, people consider it packets, network guys.
Now, so, I'll say it again. In reality,
even though, yeah, technically it's called, at layer 2, it's called a datagram. No. Data link? No. Frame, sorry. Frame, that's what it's called.
TCP/IP model, which is this, but for reference, I'm going to use the OSI model. So I'll add in those extra layers, the session layer and the presentation layer. Just gonna add those in there, stack them up. And if you want to follow along, which I highly encourage you to do that, it's really helpful to watch this actually happen, use your own computer. So I got a link below, download this packet tracer file that I'm about to walk through. Go ahead and do it right now. I'll wait for you, if you pause. Otherwise, here we go. So using simulation mode, we'll watch Johnny go all the way across the network to access networkchuck.coffee, which is this server right here, and order some delicious coffee. So let's click on simulation and watch this in bullet time because it's amazing. Now, as we go through this, I want you to notice one thing. I have our traffic filtered, meaning that I'm only looking at HTTP and HTTPS traffic, web traffic, things you might use to access a website. I'm telling you this because you won't see things that we saw in the last video, like ARP requests to discover a device's MAC address. You won't see a DNS query, so Johnny can discover the IP address of networkchuck.coffee. If you want to see those things, you can. Just go edit the filters right here. You can unlock all those goodies. So we're going to open up Johnny's laptop here. We're going to navigate over to his desktop and click on web browser. We're going to type in https://networkchuck.coffee. And go. Now, nothing happened because we're filtering traffic. Let me step forward in time and watch things happen. There we go. So we see here we have our blue message, our blue packet that Johnny's getting ready to send out. In our simulation panel here, you can actually see we have 2 separate messages. Why? Well, one is what he's getting ready. The other is what he's sending out to the switch. Let's open up that first one and take a look. I'll just select that first message right here. You can see we have our wonderful 7 layers of the OSI, even though we're actually using TCP/IP. Again, I'm telling you, the networking world always uses the 7 layers. Always. So let's analyze this. First, Johnny starts out by using layer 7. What's layer 7? It's our application layer. What application is he using? Well, we got a message right here. Because we have that layer selected, the HTTP client sends an HTTP request to the server. What that basically means is that Johnny's web browser is attempting to access a website. So simply, this is the application layer. The protocol we're using here is the HTTP protocol. And actually, we're using the HTTPS because it's secure and encrypted. But this is an example of an application layer protocol that is used by things like, hey, your web browser. You're using that right now. So Johnny types in networkchuck.coffee into his web browser. He hits enter and his computer gets to work. And so again, the application protocol we're using is HTTPS. And the computer takes this data and gets it ready to send out. Now at this point, the computer's goal is to get the data all the way down through the layers, down to the physical layer, so it can go across our Ethernet cable through the internet to the other server, to the networkchuck.coffee server. But what's happening in all this mess? What's going on? Let's talk about it. Now we're going to skip these 2 layers for now. We will go into more detail later. But again, typically they're meshed into the application layer anyhow, so it's okay. Looking back at Packet Tracer, we're on to layer 4 now. Layer 4 is our transport layer. For now, the way I want you to think about it is how can we transport the data? How can we get it there? And we really have 2 main options. We can use TCP, or UDP. Now, I'm not going to cover this super in depth right now, but just know that when we use TCP, it's more reliable. It's when we want to make sure our message actually gets there. We have mechanisms in place to make sure that if it doesn't get there, we can send it again. Whereas UDP is not as reliable as TCP, and it's typically seen as a faster transport method. So when it comes to the transport layer, these are the 2 main options we have, and then we have our ports. Now, the destination port here is destination 443. You might recognize this port. 443 is reserved for HTTPS traffic. You might also be familiar with port 80, which is HTTP traffic. Again, we'll cover more in detail later, but just know that that's what's happening right now. So we'll move on down through our data real quick, put our data down here, and the transport information we're going to use will slap on as a layer 4 header. We'll attach that to our data. And inside this header are things like, hey, we're going to be using TCP, and we'll be using port 443. Now, what just happened here is important. The process of taking our application data and then scooting it on down here and slapping on that layer 4 header, that's called encapsulation. This encapsulation process actually happened up here as well. The web browser encapsulated whatever Johnny wanted to send to the networkchuck.coffee server, which is him saying, get me some coffee. It's a message saying, get me some coffee. He encapsulated that into a HTTP header, which is our data. The way I like to see this is, let's say, for example, the data is like a message, a letter. We encapsulate that message into a HTTP header, which is our data. When we moved on down to the transport layer, we took that data envelope and we put it inside another envelope. We encapsulated it. And this new envelope has our data inside, and this is our layer 4 header. And that's the way I like to visualize encapsulation. We'll keep taking our letters and just putting them inside other envelopes, other letters, until we get to the bottom, which is our data link. And I'll show you. Oh, by the way, this message right here, when we have our data encapsulated with a layer 4 header attached, we call this message a segment. And now we're getting into familiar territory. We're at layer 3. Layer 3, again, is our network layer. And if you watched the previous video, you know that layer 3, we're dealing with IP addresses. We're dealing with routers. Love that stuff. So in this layer 3 header, we see that we have our source IP address and we have our destination IP address. This IP address being Johnny's IP address, and this IP address being the IP address of the networkchuck.coffee server. So we'll drag our segment down onto layer 3, and we'll encapsulate that segment by adding a layer 3 header. And again, our layer 3 header is going to contain the IP address information, and we're basically telling our router where to send this. We're giving our router directions. We're saying, hey, Mr. Router, here's my source IP. This is who the message is from, which is 10.1.1.3, and then the destination IP address, which was 23.227.38.65. Now let's test your memory. You would have learned this from the last video. What is this new message we have? What is it called? What do we call it?
Packet.
If you said packet, you're absolutely right. A packet has all the layers above it, the transport, session, presentation, application, all those layers encapsulated with a layer 3 header telling the router, hey, here's where you send this info. And now we're at layer 2, almost there. Layer 2 is our data link layer. With data link, our layer 2, we're dealing with MAC addresses. We're giving our switch directions to the next stop that our information is taking. In this case, it'll be our router. Here we have the MAC address of Johnny's laptop, and here we have the MAC address of the router. So now we'll move down our packet into layer 2, and we'll slap on our layer 2 header. And layer 2 will also have a trailer as well. And this will encapsulate it into a message that we call, well, what do we call it?
Frame.
What do we call messages that deal with layer 2, that deal with MAC addresses and switches? If you said frames, you got it. This message is indeed a frame. A frame has all these layers encapsulated down, and inside these layer 2 headers, we have the directions for the switch. Tell the switch where to send his message. So in this case, we have the source MAC address, which is Johnny's MAC address. And then we have the next stop, the destination, which is our router. And that's pretty much it. We've encapsulated all the layers down to a frame, and now we can send that frame over the physical layer, the Ethernet cable. So he hits the wire, and boom. And actually, he's up here. So he goes from Johnny to the switch. Let's watch it happen in Packet Tracer. If we step forward in time, we see that frame go to the switch. If we open up that frame, we're only seeing layer 1 and layer 2 because the switch can't see anything else. All these layers right here have been encapsulated down into this frame. And when the switch receives this frame, it's got this bulky envelope. And we see that encapsulated all the layers down. Down to a frame, and now we can send that frame over the physical layer, the Ethernet cable. So he hits the wire, and boom. And actually, he's up here. So he goes from Johnny to the switch. Let's watch it happen in Packet Tracer. If we step forward in time, we see that frame go to the switch. If we open up that frame, we're only seeing layer 1 and layer 2 because the switch can't see anything else. All these layers right here have been encapsulated down into this frame. And when the switch receives this frame, he's got this bulky envelope, but he only opens the first envelope. And he opens up and goes, oh, well, it's going to this MAC address, which if I look in my CAN table, my MAC address table, I can see that MAC address belongs to this port. I'm going to send it out this port. That's where the router is. See right here, he looked it up, and Fast Ethernet 06 is the port that the router belongs to. Let's step forward in time and watch it happen. Boom, it goes out to the router. And boom, it also does it here. If we open up that message, the router did indeed receive a frame. And he made sure that it was for him. It came to his MAC address. He will then do the opposite of encapsulation. He'll de-encapsulate it, which basically means he opens the next envelope to see what the next layer says. So he takes a peek at layer 3. And at this point, we're dealing with the packet, with the layer 3 header, the layer 4 header, and the data. The router looks at the layer 3 header, sees where it needs to go. What is the destination IP address? Looks in his routing table. He's like, yeah, I know where that goes. I've got my map. I'm a layer 3 guy. And he then proceeds to send it out to the switch. Now, something important happens here. Remember, the switch can only deal with layer 2. If you recall from our previous videos, the router has to somehow tell the switch how to get to networkchuck.coffee. He has to tell him his MAC address. Otherwise, the switch will have no idea where to send it because he can't see IP addresses. So after the router learns the MAC address of networkchuck.coffee using ARP, he encapsulates his layer 3 header, which is the IP address information, inside a new layer 2 header. And he changed the source and destination MAC address. And he had to change it because before, the message he received, the source MAC address was Johnny and the destination was himself. Now he has to change it to being the source is himself and the destination is networkchuck.coffee. So he encapsulates that, it's now a layer 2 frame, and he sends it out to the switch. We'll step forward in time in Packet Tracer here. The message arrives at the switch. If we open that up, here we are again, switch eyes. We can only see layer 2 and layer 1. The switch looks in his CAM table, his MAC address table, sees that, hey, networkchuck.coffee does indeed live on Fast Ethernet 01. That's where I'm going to send that sucker. That's where I'm firing the electrical signals. And he does that. Let's watch. We step forward in time once more. Boom. The frame goes to networkchuck.coffee. If we open that message up, we now have all the layers once more. And here's what just happened. The switch sent this frame to networkchuck.coffee. Now, because the server that runs networkchuck.coffee was built obeying the guidelines of the TCP/IP model, when it receives a frame, it knows exactly what to do. It'll first do exactly what the router did. Look at the layer 2 header. Make sure that, hey, this is actually for me. It's my MAC address. Hey, cool. He'll take a look at the layer 2 header. He'll open up that message and go, oh, yeah, this is my MAC address. It's to me. Awesome. He'll then de-encapsulate or open up the next message and look at the layer 3 header and go, huh. Look, it's for me too. This is my IP address. Awesome. He'll then de-encapsulate it once more, opening up the layer 4 message and going, oh, hey, we're using TCP. Oh, and awesome. I love 443. We're using port 443. And then he sends it up to the next layer. And then finally, the last layer, the application layer, opens up that last message and goes, oh, it's for me. HTTPS. It's browser information. It's website stuff. Awesome. So real quick, a 1,000-foot view. What Johnny had to do is he had to use the entire TCP IP
Okay, explain everything. You have 2 minutes. Quick. Okay, so Johnny sent using HTTP again. Has to use a router. Has to use IP. Has to use layer 3. The 7 layers: application, presentation, session, transport, data link, physical. Let's talk about the process of sending. First, he creates his packet, encapsulates. Encapsulates when you create. De-encapsulate is when you receive. Encapsulate, send. De-encapsulate, receive. He encapsulates the message by first, of course, adding the protocol HTTP. Then inside of that, he, of course, has to talk about the presentation, which would be SSL, protection. Now, again, this is data. All of this is application. It's just data. It's not layer 7. You don't see all of them. Then you see transport, which would be TCP or UDP, TCP reliable. Then network, we know the IP already because of DNS. Our DNS server exists somewhere. And yeah, I'll do the rest off stream. I'm going to take a longer break now. I've hit my 2-hour mark. I'm going to clean the kitchen, eat, then do another hour. And then I have to go do, well, right now, first, no bullshit. It's going to take like a 5-minute relaxation break. Then do the kitchen real quick. Then eat and then work on the garden. And then when I'm back, again, unexpected periods could come up. I have to do an extra hour of just crypto, and then I will end the stream. That's my essential time every day. Beyond that, I have to do more, yes, but it's non-essential, and it's more about a lifestyle that I'm trying to incorporate. But this is sustainable and will get me to reach my goal, and I can keep following it. 10 a.m., first thing in the morning, study. Throughout the day, you want to try study more, of course, but it's not, this is a mandatory stream. Do the thing that you can do on your worst days, my motto.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you'll come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you'll come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you'll come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
What will you do?
Rebuild it. Just the way it was, brick for brick.
What does that mean?
Rise.
I broke you. I hope you come back.
Why build yourself?
I'm not meant to die in here.
Here, there. What's the difference?
One of the most difficult challenges in the market isn't spotting signals, it's managing conflicting ones. I'm sure you've seen it before, where one signal screams a bullish breakout and another warns of potential danger ahead. And what's even trickier is juggling different timeframes. But conflicting signals and timeframes is just a part of the game, so what do? If you can't navigate these mixed messages, then you'll either freeze and get stuck in the market or get completely chopped to pieces. So in this video, we'll break down how to read these signals and uncover what they're really telling us about where the market may be heading next. Before we do, quick reminder that I'm not a financial advisor. Always do your own due diligence and research, and past results are not indicative of future performance. And if you are a brand new subscriber, massive shout out to you. I'd highly encourage you to join us in the Investor Accelerator community. It's completely free, and you can get your hands on the next edition of our economic, Bitcoin, and altcoin report. There's a link in the description below where you can drop your details in. I'll kick this video off looking at market sentiment, and specifically these two indicators at the bottom a little bit over the last few days, where we've been seeing gains in markets like Solana and of course Bitcoin as well, whereas ETH has just been struggling around its lows somewhat, but it won't take too much for that pattern to change. We have a pivot point at around $4,500, which ETH is getting very close to breaking back on top of. So if we can see our daily downtrend break and a higher low above that $4,500, then ETH may very well be testing all-time highs sooner rather than later. On the underside of the market, we have the same 50% level at $4,150 and the pivot point at the even 4,000 psychological level. So anything above this zone is still relatively safe for the higher term timeframes, but if we see a breakdown beneath that level, followed by close and lower highs, then look out for a continuation down to the mid $3,000 range. Over now to Solana, which in all this selling pressure in Bitcoin and ETH and many other alts, Solana has remained in its daily uptrend. It did push lower for a few days off this recent peak, but it did not break any trends. It held on top of its 50% level from its all-time high down to the major correction bottom. That price point came in at $195, and since then it
Hey guys, how are we doing? Crypto Insight UK here, bringing you back another YouTube video. So first off, let's just discuss this. This is what I'm thinking as a potential scenario right about now. Government shutdown, markets wobble, Bitcoin takes liquidity, equity markets pull back a bit, everyone panics, the top is in, becomes consensus, then the government reopens, liquidity comes in, ETFs approved, big Q4, Bitcoin 150k by the end of the year, alts rip. I'm saying this because JD Vance has come out and said, look, there's an 80% chance of a government shutdown. We also then saw yesterday from Eric Balchunas, let me just quickly find that tweet. We saw that he basically said there's a 100% chance now that ETFs come through. Did I retweet it? I'm pretty sure I did. Eric Balchunas. Yeah, he's basically saying here, honestly, means the odds are 100% chance that that ETFs come in. Then he's saying Solana is probably first. I think they'll probably approve Solana and XRP and probably Litecoin at the same time, because this was his tweet yesterday here. He said the final deadline for Litecoin, Sol and XRP is the 2nd of October for Litecoin, the 10th of October for Solana, the 17th for XRP. And he said, who's ready? Spot ETF deadlines of this week. Litecoin, Solana at first. Should be a wild month. It kind of plays into that thought process. Look, if he thinks Solana is going to be first, maybe they'll deny the Litecoin one, or the government shutdown will happen and there won't be any decision made. They'll come back and just be like, boom, boom, boom. They're all in with an increase of liquidity. It's just a potential catalyst. Like what I've been saying is, I think there's going to be some catalyst. Yesterday, I presumed maybe, I'd not presumed, I just like indicated that maybe it was like because of war or something, because we saw like US bombers moving. Let me see if I can find that tweet. We saw US bombers moving and we saw like different things in the Pentagon, and we discussed that in yesterday's video. I think something's coming just to have this last little flush out in the markets here, take Bitcoin down into this 106k liquidity that I've been discussing since July. As I said, if that gets taken, I'm going to be so much more bullish. Like, I'm bullish anyway, bullish the medium term, bullish the long term, and just that's the only like short-term concern that I have is that liquidity. And I've been saying that since July. You've been saying, you'll notice if you've been watching me on this channel, what have I been saying throughout this whole period here when we've just been chopping it around for Bitcoin? I've been saying I don't know what's going to happen next because of this 106k liquidity is my main concern to the downside, but that I am long, like I'm bullish. Yesterday we obviously did close my Doge trade, and that is because if we get this 106k, I'd rather have a 5 to 10% better entry, and I will deploy everything that I already had in that trade back in. I also am completely still spot positions. I've not sold anything. And because I think we're going up, and I'm going to discuss why in some other charts now as well. Obviously, I'll give you one last look at Bitcoin's daily liquidity. This whole period here, that's from July that we've been chopping about in this area. So I'm not surprised people are fed up. This is July. Look, we've just basically gone sideways. Yeah, look, we made a higher high, and then we made a lower low, and then we made a higher low, and then we made a higher high, and then we made a lower low, and then we made a lower high, and now we actually made a higher low. And so everyone's probably sitting there thinking, oh, maybe it is a bottom, like, because you could go like this, look, oh, there's a low, higher low, like maybe the bottom's already in. What are we going to do? I personally think, I don't really know. Again, like, I don't know what the next few days or weeks hold, but after that, this liquidity is going to get taken inevitably above us. That's what I've been saying. And it's just so much easier for it if we take that 106k. So that's what I'm looking for. Now, going on to the BLX chart, this is Bitcoin on the monthly, okay? And we're going to discuss this. First off, I'm going to draw upon Raoul Pal's recent video with Julian Patel. They basically suggest that liquidity is a year out, like a year later, because of debt refinancing that they didn't pick up on from 2021. It's normally like 4 years they have to refinance the debt or something like that. along these lines, I'm just paraphrasing. I think you should go and watch that video. Put it in the newsletter. I talked about it yesterday. I said, I think, look, it's a crucial video to watch. Raoul Pal's recent video with Julian Vattel, where he breaks down the everything code and gives you a whole presentation with data supporting what he thinks and why. So if he thinks that let's just say we're a year behind cycle-wise. This should be cycle top, 2025. Cycle top was 21. Cycle top was like 17 just into 18. So 25 into 26 should be cycle high if we weren't a year out. And so let's just discuss this. So if we are a year out, where does that put us? Let's have a look. A year out from the highs in previous cycles. This is December 2017, obviously into 18. So we'll go back a year to find we'll find December 2016. Let's see if this is it. Yeah, December 2016, January 2017. And then we'll find this is 2021. And look, you can say the highs are here. So we'll find 2020, December 2020 here. This is it. And then look, so this is what it would be like if it was a year before. And look, pretty much from like 2013 cycle, we didn't, like, there's not a lot of data, but we can use 2012 if you want to. 2012 here and January of 2012. So that'd be coming into the end of this year. And obviously right now we're obviously only in October. So if we find October specifically, let's find it there. October is here. Let's find October specifically. It's this month here is actually red in this cycle. And if we find October specifically, that's November, October, that is here. So that would be September going into October is these circles here, this circle, and this circle. And so where does that line up in the RSI? And I'll show you that as well. Because I'm just showing you, I'm just going to try and build a little case here to say, look, maybe he's right, maybe he's not. That's going into October. So this is the month of September. I'm going to take you on to September because that is the month we are in right now. September and September. Cool. So realistically, look where the RSI is. It just peaks into the overbought area. This is obviously all the way back in 2012. The RSI is below the overbought area in 2016. And in 2020, it has a dip. They all dip as well, by the way. Dip, dip, dip. That's like you playing that game at school. You're like dip, 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 and then whatever. I don't know why I just said that like that. Anyway, so what you can basically say is this price action is essentially here, like all we've had so far. This is the discussion that I'm trying to make today. What we've had so far in here is just essentially this. It's a choppy mess. It's this. It's this. That's what you can basically suggest. Should Raoul Pal be right? And look, I'm not here to say Raoul Pal's always bang on, but I am here to say that he provides so much data and directionally he normally has the area of travel pretty decent. Doesn't necessarily get the absolute top, but he's projecting that by next year, he's saying by Christmas we should be at 200k, and by some point next year was where he thinks that if we just use liquidity, only liquidity, and he said that it's basically the indicators from what that means on the market are still rising and they're yet to top out, and he looks 9 months into the future. So he's saying that even 9 months out, he hasn't yet seen the exact top with his liquidity indicators and his forward-looking indicators. He's discussing, right, so even 9 months out, we're not at the highs. So he's saying, look, liquidity is lagging by about a year because of different things, and you need to go and check out that podcast. But let's say he's right. And he said 200k by the end of the year. And he said, based based on 9 months forwards, we'll probably be around 400k, potentially if it goes further up to 600,000. And look, I'm not saying, as I said, I'm not saying he's right. I know he called for ETH to go to 10k last cycle and it only went to 5. I get that. So let's say he's half wrong. Bitcoin still goes to 200k next year. Like, and this is the thing, is like, so let's say this area is where we are. This area is where we are. This area is where we are. And you can say, look, laws of diminishing return, but let's just for the sake of an argument here, I'm going to bars pattern all of these different potential options for price. And look, it's not going to be bang on, but I'm just going to show you realistically what could come here for Bitcoin. These are the scenarios. I'm not saying that these are accurate by price, but what I am saying is if we are that year behind, every single one of these, and I'll move them again so we can see the different 3 scenarios. This is the lowest. It would take us out to 319k. Actually, it's not even accurate, so let's just bring us down a month. There. It would take us out to 300k. This would take us out to 800k. I'm not saying this is exactly what's going to happen. 3 million for that one if we did the same returns we did in 2014. Again, just hear what I'm saying. I'm not saying this is going to happen, but what I am saying is clearly if we repeat any sort of those cycles, which it does look similar to those cycles, then we should see significant upside. Now there's something else to back this up as well that I've discussed over on X today, which is the Russell 2000, and that's something that Blockchain Backer has been discussing, and it's a great thought from him. But one thing that he's been discussing recently is that he thinks the top could be in. He's been playing devil's advocate for a few different reasons. I'm going to get into one of those thoughts. He's said a few weird things though recently. I do think the market's got to him a bit, because he said, all the KOLs on Twitter like are bullish because of engagement, but anyone who posts bearish posts at the minute is getting the most engagement. So I don't really understand on that one. You can literally see that based on literal impressions. Everyone can see that. You don't need like his back-end data to see that. But one of the things he's been saying is, look, the Russell right now, I'm going to talk to you about it. Oh, look, we've made 3 peaks. It's not really showing strength. It hasn't managed to break out yet. I'm worried about it, etc. Fair enough, fair thoughts. But if we look back to this cycle here, which is 2018, finishing here here really in 2020, which again is 5 years ago now, not 4 years ago, which would kind of coincide with what Raoul Pal said. What we've got is 3, this is on the weekly, the Russell 2000, you can go and check it yourself, 3 lower highs here, which we haven't actually had this time, but 3 almost equal highs, like very close to the highs. And on the third time, the interesting part is we had this V bottom, which is obviously C19, this V bottom and then recovery and then a breakout. We went to the 1.618. Have this last little flush out in the markets here, take Bitcoin down into this 106 down. We also then saw yesterday from Eric Balchunas, let me just quickly find down.